Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video. All math basic course, and as always, it is an honor and a privilege to be serving you today, as it is every day here in my virtual classroom. Stepping aside as we get into the second half of Chapter 4 with radicals and rational exponents. This is Section 4.4 on solving radical equations. You know radical equations with the square root, cube root, something like that. This time your variable, let's say x, is inside of there. We got to get it out, or at least we got to solve for it in some way. Normally getting it out is the way to do it. How do we get it out? Well, the lecture portion is going to tell you about that here in just a moment. We're also going to be learning about when some solutions shouldn't work in these things as well. That's actually the nature of these kinds of problems. Now, if you want to hear the lecture portion, I'm going to get into it right now with the downloading the PDF down below if you'd like to do so. But if you'd like to jump to the problem set, which is problems 3 to 63, at least that part after the vocab and concept check, you can find the timestamps down below as well. Without further ado, I'm going to go ahead and get started. We're going to solve equations containing radicals and rational exponents, and then we're going to solve radical inequalities. Actually, didn't know that. We're going to solve radical inequalities. Radical equation, sure, that's a new core vocab term, but this other term, extraneous solutions, is here. I'm sure I've said the term extraneous before, even in IM2 and such, but this might be the very first time they're introducing that actual phrasing. This is not the last time you're going to hear it as well. There are other function types that can introduce extraneous solutions. They'll be talking about it. We'll be going over it. Let's go ahead and get started. Equations with radicals that have variables in their radicands are called radical equations. Here's an example right here. Now, the basic essence of solving these is to isolate the radical on one side of the equation. You want to get this thing by itself. No 2 in front, nothing added or subtracted around it, just getting the radical by itself. Trust me, it's the way to go. And I'm sure we're going to look at an error analysis question that's going to say they didn't do it and then they made this mistake. And then you need to raise each side of the equation to the same exponent. So if, first of all, this is a square root, so then you need to raise them both to the same power. In this case, you'd probably want to square both sides, something to eliminate the radical. Okay. And then you're going to solve the resulting equation using techniques you learned previously. Maybe it's solving just a basic linear equation. Sometimes you got to solve a quadratic, maybe by factoring, whatever it is. But from that stage, you're going to solve. And they say check your solution. This is super duper important. We're going to check probably every solution early on, at least in the lecture portion. And then when it comes to the problem set, maybe we'll learn the patterns as to when we should be checking and when we shouldn't be checking our solutions. I'll make sure to talk about those. So 2 examples. Oh, it's the same example here, same equation. To solve this thing, step 1 is to isolate the radical portion. This square root of x plus 1 we have to get by itself. Did a Dodger just homer? Come now, who is that? Anyway, so divide both sides by 2 to begin with. 2 is multiplying by it. Divide both sides by 2, now it's by itself. That's our step 1 complete. Step 2, like I said, because this is a square root, we should square both sides. This is like the opposite of when x is squared. Then we take the square root, right? Now this is the opposite here, squaring both sides. The difference is when you take the square root of both sides, that other side gets a plus or minus or whatever. This time when we square both sides, whatever this was, will just turn positive, period. Now squaring this side just gives you the x plus 1 itself, and conventional method of solving, subtract 1 from both sides, you get x equals 3. Double check it, it seems to work out. The left side does equal the right side, good to go. This next example, cube root of 2x minus 9, and then minus 1 equals 2, we want to isolate the cube root of 2x minus 9. So we're going to add 1 to both sides to begin with here, and then to cancel out the cube root portion, we will cube both sides. Now, cubing a number will keep its sign and won't turn it positive. If it was negative, it'll actually stay negative. So you cube both sides right there, add 9 to both sides, and divide both sides by 2. We get x equals 18. Double check that one. It also seems to work out. So pretty good stuff to start. We'll also do some real-life problems. With this one here, they give us a model for mean sustained wind velocity inside a hurricane, where P is air pressure. They said estimate the air pressure when the mean sustained wind velocity is 54.5 meters per second. So nothing like difficult. They're just saying, here's the equation, substitute something for V, and solve for P. P is inside the radical. So first thing we're going to do is isolate this radical by dividing by the 6.3. Looks like they did a little early rounding. You'll know I never do that. Because it's a square root, they're going to square both sides to get this part by itself. 86.5 squared is this, or at least rounded. And then they use their means to solve for P, where they get 938 millibars of air pressure. So only difference here is we just got to use the model to do a substitution and get units in the answer. All's good there. I don't see a double check on that one. I think for a word problem like this, they're not going to try and trick you and go, no, that solution doesn't work. But down here, they're going to start talking about certain solutions that would not work potentially. Raising each side of an equation to the same exponent may introduce solutions that are not solutions to the original equation. Let me re-emphasize what I just stated. Before squaring both sides or whatever, solutions that were supposed to be would have been. But once you squared both sides or cubed both sides, I want to first really talk about squaring. You might have altered the essence of the problem. You might have altered what now can be newly introduced solutions that never were supposed to be in the first place. These solutions are called extraneous solutions. When you use this procedure, you should always check each apparent solution in the original equation. Now, this thing, I started to see it on this side. Here's really why this works, right? You have an original equation that says square root of x equals negative 3. Well, guys, what can we take the square root of to get negative 3? Nothing, right? There's no x value we can take the square root of and get a negative answer. But if I squared both sides of this equation, it would say x equals 9. The square root of 9 isn't 3, right? So 9 wouldn't work inside of here. Now, why are we getting x equals 9 as an answer? Well, we squared both sides. But why did it become a solution and it wasn't before? Because when you squared both sides, negative 3 turned positive, right? What before wouldn't have been a solution, right? Imagine we tried to solve by graphing. We get y equals square root of x as this equation right here. We get y equals negative 3 as this equation right here. Well, those two lines never intersect, right? This curve right here never intersects with it. Because it doesn't know whether the negative 3 is positive or negative when it squares it. What happens when you square both equations? You get y equals x, which is just a line like this, and you get y equals 9, which is a line like this. And suddenly, they intersect now. Well, they never would have intersected before. Squaring it suddenly changed the nature of this negative and turned it positive, and it didn't know. Now, guess what? If this was negative square root of x, they would have intersected together. If this was a positive 3, they would have intersected together, and those solutions wouldn't have been extraneous. So the fact that this was negative and we squared it to turn it positive is what introduced an extraneous solution to this thing. When instead it should have been no solution. No real solution, at least. Okay, let's look at an example here. Solve x plus 1 equals the square root of 7x plus 15. Now, notice that there is also an x on the outside of the radical, okay? There is an x on the outside of the radical, but our goal, it's not to solve for this x here. Our goal is to get rid of the radical where there's an x, though, here. So we need to make sure this is isolated. It is. So we need to square both sides. Boom, because we have a square root there, right? When you square this side, this linear becomes a quadratic. Remember, it's a special perfect square trinomial. And then we're going to solve this quadratic. You subtract 7x and 15. It looks like you factor down and solve using zero product property. You get x equals 7 and x equals negative 2. Let me move my ugly mug right here, and let's get to checking if 7 and negative 2 work. Well, 7 does work. You plug 7 into, by the way, the original equation, or should I say an equation prior to squaring. Plug it into, and this is the only thing we have, plug it into here. If you do it after squaring, that doesn't work, right? These solutions work once it's squared. Maybe when it's not squared, it might not. But 7 always seemed to have worked. Negative 2, however, doesn't. Negative 2 plus 1 is negative 1, and plugging negative 2 here, you get positive 1. Negative 1 doesn't equal positive 1. But if you notice, if you squared those, it would say 1 equals 1, and then you'll see that it works. But it doesn't work here. In the original equation, negative 2 don't work. Negative 2 is extraneous. So the only solution is actually just x equals 7. So the idea behind that once more, and I don't know, I don't see any graphs on these. Normally they'd use a graphing calculator to show, so I'll try and give it a look-see. Why did this happen? Because this x plus 1 originally by nature was some linear equation, right, like this. And this square root equation, let's say it looked something like, I don't know for sure, let's say it looked something like this, right? They only intersected at one place, and that one place was probably just x equals 7. But then you squared both equations, and what happened? Suddenly, this x plus 1 equation turned into a parabola. And a parabola now comes back upward, and then this 7x plus 15 equation in green maybe looks like this, and suddenly there are two solutions. There's negative 7, or there's 7, and there's negative 2. Well, negative 2 was never a solution before here. Maybe it would have been if there was this portion, right? Maybe suddenly negative 2 would have been, but it's not there, and we don't know what's happening as a result of squaring when something turns into something else, right? And that is the nature of why this happens. All right, let's solve an equation with two radicals. Now, your goal is once again to isolate a radical on one side of the equation. Check. It's isolated. It's by itself. We'll square both sides. Listen, this radical is not on its own side of the equation, and when we square it, you'll see what the issue is as to why we do want a radical isolated. Squaring this is going to cancel out the square root, but squaring this leaves you with a perfect square trinomial, a squared plus 2ab plus b squared. Well, guess what? We still have a radical there. This is why we need it isolated when we square it. Otherwise, a radical will always remain in what you do, and you're just going to make your thing bigger. But we had to isolate one of them because guess what? We have improved our situation. We actually now just have one radical instead of two. We've improved our situation. So what do we do now? We isolate this radical. We subtract 1, we subtract 2, we subtract x, and then we divide both sides by 2, and then we get this by itself to square both sides again. Boom. Now we're in our right stage, right? Now we're in our right state of mind. Square both sides, we get a quadratic. We solve this quadratic, zero product property, and we get 2 and -1. Double check them, and we get extraneous solution on 2. -1 seems to work just fine. They're showing you here as well, right? These were probably the two original equations. Finally, they're giving you one here. These were the two original equations. You can see -1 works, boom, like that right here. And it appears that if these were full sideways parabolas, probably like this, and like this, that x equals 2, I didn't draw them very well, but, if I did like this and like this, x equals 2 would have made sense as an answer. Because squaring it turns it into, you know what I mean, right? That's the idea. These could have been full parabolas because they could have had a negative portion and squaring them. I'm getting too deep in that talk, but I'm explaining why these come into play after squaring them. And we squared twice. We turned original square root functions into full parabolas, into full quadratics. So there's that. I want to really make sure you're understanding the rational. Not rational. I just saw the word rational here. Extraneous stuff. Now, if you'll notice, well, we'll talk about it when we get to the problems. Okay, solving an equation with a rational exponent. Let's solve this thing. Same first step, get this thing by itself. So turn that into this by subtracting 2 from both sides. Now, we have to cancel out this 3/4 exponent. We'll raise it to the 4/3 power. Why do we raise it to the 4/3 power? Well, we can see it in a couple ways. We can see it in what this actual property is. Remember, a power to a power means that those would multiply. 3/4 times 4/3 does equal 1, right? And 2x to the first power is just 2x. That's why we do that. But also, if you think about it, 2x to the 3/4 power is the 4th root of 2x cubed. So what are the two things we're going to have to do here? We're going to have to take the cube root of both sides, this side, right? That cancels out the cubic portion. And doing that is also raising to the 1/3 power. That's where the third part comes from. And then we'd also now have to raise both sides to the 4th power, like that, 4th power, and that's the same thing as getting that 4 all up in there, and that's where that comes from. So both of those parts happen to cancel those things out, so multiply by the reciprocal, raise it to the reciprocal exponent. And then we simplify and solve, and you double check that one, and it seems to work out as well. We haven't hit the inequalities yet. We'll see when that pops up. Let's take a look at another example. X plus 30 to the 1/2 equals x. You can also say x plus 30 to the 1/2 is the square root of, if you want to do that. That's why they're squaring both sides. And they're solving this. They get 6 and -5, and -5 doesn't work. You've probably noticed that it seems one solution generally is not working. That's not always the case, but that's often the case. So just keep that in mind, that when you get two solutions, go, are they both going to work? Not always. They can. It's possible. Trust me, I can make an equation pretty quickly that does that. All right, solving radical inequalities. A radical inequality has something like this, less than or equal to, something like that when we solve. When we isolate the radical, divide by 3, we will still square both sides to solve. We get x is less than or equal to 17. Still follow the rules of inequalities. The one thing about this one, though, that's a little different is you have to still understand your domain. X can't just be any number less than or equal to 17. Is x allowed to be 0? 0 minus 1 is -1, and you can't take the square root of a negative. Understand your domain. Understand your domain for this one here. X minus 1, oh, they read it right here. X minus 1 has to be greater than or equal to 0 because you can't take square roots of negatives. So x still has to be greater than or equal to 1. So your final solution set, the less than or equal to 17 does apply. x is less than or equal to 17 will work and fit within here, but you have to still follow your domain. So it needs to stay within that restriction. I'll probably start with the domain first when we talk about it in solving. Yeah, and then we'll go from there. Okay, so that's the end of the lecture portion. Let's go to the vocabulary and core concept check. Number 1, vocabulary. Is the equation 3x minus root 2 equal root 6 a radical equation? Explain your reasoning. It's not. It's not. See, radical equations have your variable in the radicand. So this is not. Doesn't matter that it has irrationals. The variable is not in the radicand of the equation. And if you're confused about that, think about, a question like this one where I have something like, x plus 2 squared equals 9, and I say solve for x. Is this a quadratic equation just because 2 is squared? No. And, 2 squared is 4, x plus 4 equals 9, and x equals 5. It was a linear equation, right? A constant being squared or square rooted means that, okay, x may be an irrational solution. It doesn't mean that the function is a radical equation, or, that when I graph it, it's not going to make a square root graph. It's going to be linear in that one. Explain the steps you should use to solve square root of x plus 10 is less than 15. Well, I'll also show you them. I'm going to first I'm going to do the domain check in this one, because when it comes to the less than stuff, we're going to talk about an infinite number of solutions that will end up being less than whatever we're talking about. So with respect to the domain, guys, our inside of our inequality must be greater than or equal to 0. And that's straight up our domain. So we have to restrict this. X must be a positive number or 0. Now, that's the first part. Do I have to start with that? No, but I have to consider it. I'm going to subtract 10 from both sides to isolate my radical, like that, and I get 5. And then I'll square both sides, and then I get 25. X is less than 25. So, So x has to be greater than or equal to 0, but less than 25. I know I didn't write out the steps, but I'm giving you them. So step 1, right here. Step 2, isolate radical. Step 3, square. Step 4, write your final solution as a compound inequality. So any numbers here, the greater than or equal to 0 will keep these as real numbers. The less than 25 will keep this inequality intact. It'll keep it as true statements. All right, guys, so we are going to go ahead and go to the vocabulary. We just did a vocabulary core concept check. We're going to get to problems 3 to 63, the main problem set. They are downloadable below as well. Follow along, please, if you'd so choose to. Let's go ahead and get started. I see an elephant, but we're not there yet. In numbers 3 through 12, solve the equation, check your solution. Well, if they say check, I suppose we're going to have to do so. Maybe we can seek out a pattern and say when should we officially check and not. The square root of 5x plus 1 equals 6. Let's solve that. To begin with, understand the radical should be isolated. It is. So let's now square both sides. I am squaring because it is a square root that is there. So we get 5x plus 1 equals, and this is 36. Subtract 1 divided by 5, and we get x equals 7. Now let's double check that. Make sure all's good. We'll do this on the side. We'll do square root of 5 times 7 plus 1 equals 6. Just keep the 6 on that side. Square root of 35 plus 1 equals 6. Square root of 36 equals 6, and 6 equals 6. This checks out. All good. Number 4. The square root of 3x plus 10 equals 8. Once again, the radical is isolated, which is good news for us. It is a square root, so to counter that, we will be squaring both sides. So let's square both sides once again. The square root of something squared is just that something on the inside. 8 squared is 64. And we'll solve just basic conventional stuff. Subtract 10, divide by 3, you get x equals 18. Let's double check that one. We're going to have the square root of 3 times 18 plus 10 equals 8. Again, original equation. This is 54 plus 10 is 64. Square root of 64 equals 8, and 8 equals 8. That checks out. Okay, number 5. You have the cube root of x minus 16. And this equals 2. This radical is isolated. However, this time it's a cube root. So we are going to cube both sides this time. And you're left with x minus 16 here, and 2 cubed is 8. As we add 16 to both sides, we get x equals 24. As a double check of that, we have the cube root of 24 minus 16, which equals 2. And that is the cube root of 8, which equals 2. Or does it? Yep, 2 equals 2. All's good. No extraneous solutions right here. Not yet, not know-how. When will they show up? I think, like I said, we're going to have to determine patterns with them. I don't know if all of these ones will work and then later other ones won't work or something like that, because there were later examples that they introduced it. I am hoping we get some extraneous solutions so that we can talk about patterns when they are happening versus when they're not. I really do want to get into those. All right, this time, this cube root, I should say, is not isolated. We have to add 10 to both sides in order to isolate it to begin with. So we're going to get 3 when we add 10 over here. Now that it's isolated, we can cube both sides, like so, and we'll get x equals 3 cubed is 27. As a double check of that, the cube root of 27 minus 10 equals negative 7. And we get now 3 minus 10 equals negative 7. And that's true. Negative 7 equals negative 7. Try and get to the very bottom of it. Don't just say 3 minus 10 is negative 7, confirmed. Just make sure you get to the, just write this right side as it is and get to the left side. And I'll tell you what, and I said this in the lecture portion if you were there with it, there was this stage before what was in blue. Let me delete the blue for a moment. Right there. You can also do it on this portion as well for your double check. It doesn't have to be the original equation. It just has to be any portion before you raise them to the exponents. So the cubing, sure, happened here, right? It did happen here. But you can also do that one beforehand. And cube root of 27 equals 3 should still work out as far as a step that works. The only reason you may not is if you don't trust your work beforehand that you did. But the extraneous solutions that appear only appear after raising to the exponent. Okay, that's when things change. So just keep that in mind. And that's actually, I sometimes like to check on those ones more so because number one, I trust my math more so before that. Number two, things are simplified and stuff. And number three, that's where you really start to see the effect of it, say something like 5 equals negative 5 or, something like that, as opposed to just two random numbers. Anyway, let's see what's going on here. We want to isolate this. So I'm going to subtract 13 from both sides to begin with. And we get negative 24. Then I divide both sides by negative 2, right? Which will turn things positive. Square root of 24x equals positive 12. At this point, I'll square both sides, right? I'm not going to write the squaring both sides this time. Let's see if you can follow along with that. 24x equals 12 squared is 144. And then we divide by 24 and we get x equals, I think 6. X equals 6. And there's that double checking we can have, right? This time I'm going to double check within this one. It's okay to do it on this stage. This was prior to squaring. So we can do square root of 24 times 6 equals 12. And then here we'll get square root of 144 equals 12 and 12 equals 12. Now, the book will always encourage you to do the original equation. Main reason is because you could have made mistakes before it. I'm going to say that I didn't mathematically, but you can see where more work would have been had if you did. This one was fine, though. Now, there are some where I want to anticipate when I believe we'll have extraneous solutions, like predict and tell you, hey, guys, I think this is it, so we can start picking up on those patterns. Like, how did you know that, Mr. Robinson? We'll see. Anyway. Okay, so here, same thing. We're going to isolate this guy. Let's first add 15. And then we'll divide by 8. And we get this. This time I will cube both sides. So now I get 10x after cubing, and 4 cubed is 64. I feel a little bit dirty as far as not showing the cubing portion. I might have to go back to it. I felt like for me, I'm good with it. For you guys, I don't want you to get to the, wait, how did this happen? So I might have to go back to showing the cubing stuff. Anyway, divide by 10, you get x equals 6.4. Let's double check that one. Once again, you can either plug it into right here, or you can do it prior to cubing, which was this stage, right? This is where the line was drawn. So right here, cube root of 10 times 6.4 equals 4. Cube root of 64 equals 4, and that is true. We're all good. Okay, number 9. We have 1/5. Ooh. Times the cube root of 3x plus 10 equals 8. Okay, let's subtract 10 from both sides. And we get negative 2. Let's multiply both sides by 5, right? That's the 1/5 multiply by 5, make them 5 times bigger. Now that's gone. Multiply this by 5, we get negative 10. Now we'll cube both sides. I'm going to write the cubed again. Let's cube both sides. We are cubing negative 10. Don't forget that negative. And cubing a negative means it stays negative. We get 3x equals negative 1,000. Divide by 3, you get x equals negative 1,000 over 3. Don't you dare round that one. Negative 1,000 over 3. Now let's double check that. Once again, you can double check with, I'm going to stay consistent. Let's keep this one blue. Double check with any moment before, I wanted that to be green. Any moment before you cubed. So if I take this equation before actual cubing happened, we had the cube root of 3 times negative 1,000 over 3. And this equals negative 10, or supposedly. 3 divided by 3 is 1. So now you have the cube root of negative 1,000 equals negative 10. Now, are we allowed to take a cube root of a negative number? Yes. Is the cube root of a negative number negative? Yes, it is. This is negative 10. So this actually worked out. There might be some pause on that and going, will this work? It does work there. It does. That's all good. Number 10, we're back to a square root. I anticipate more square roots in the future with problems, especially involving variables, but who's to say, right? They really seem to be pushing the cube root stuff quite often here. 2x minus 2/3 equals 0, and they're actually getting to like different kinds of answers too, right? It's not just about, they're getting fraction answers, they're getting things like that. Anyway, let's get this thing by itself before we square both sides. So we got into there. Let's square both sides like that. 2/3 squared means we square 2 and 3, and we get 2x equals 4 over 9. Divide by 2. How do you divide 4/9 by 2? You can say times 1/2, if that works, if that helps you. You can say 9 times 2, but you can also do 4 divided by 2. 4 divided by 2 is 2, and now you get 2/9, and that's what x is going to be. X equals 2/9 as an exacto worko. Now, let's double check that. Again, this was the squaring portion right here, so I'm going to check the square root of 2 times 2/9. And does that equal 2/3? 2 times 2 is 4. We get square root of 4/9. And the square root of 4 and the square root of 9 are what we're going to get here. 2/3 equals 2/3. Nothing extraneous yet. Feeling pretty good on things. Number 11. All right. 2 times the 5th root of x plus 7 equals 15. Okay, 5th root. Woo! So we're going to subtract 7 and divide by 2 from both sides to begin with before we mosey on over to our raising to the 5th power. Divide by 2, we get 5th root of x equals 4. Yes, we are going to raise both sides here to the 5th power now to get rid of that radical. And 4 to the 5th power, we've seen it a couple times, is 1,024, and that's your final answer. Now this would be a wonky double check here just to say plug in 1,024 and see if it works. Of course it'll work. So maybe this time let's go back to the original. I don't want to stray away from the original too often because you could have made mistakes leading up to it. So let's just see that this still works out. I mean, listen, it should. It should. The 5th root of 1,024 is indeed 4. And we got that. 2 times 4 is 8. And you get 15 equals 15. So all's good there. Lastly, in this section, we have number 12, or in this block of problems, we have number 12, and we have a 4th root. And we have the 4th root of 4x minus 13 equals negative 15. Whoa. We will add 13 to both sides, and we get negative 2. Now, when we raise these to the 4th power, keep in mind, obviously, the left side just becomes 4x, right? Yep. The right side, however, negative 2 to an even power will turn positive. Negative 2 to the 4th power is the same as 2 to the 4th power. It's positive 16. Divide both sides by 4, you get x equals 4. Let's double check this one. Let's take a look right there at this stage. The 4th root of 4 times 4 is the solution, equals negative 2. 4 times 4 is 16, and the 4th root of 16 is 2. 2 equals negative 2. Uh-oh. That doesn't work. Uh-oh. Should I check the original and see if that works? No. Something went wrong this time. Something went wrong. I'm not saying we messed up. I'm saying that this solution doesn't seem to apply here. X equals 4 don't work. Is there something else that should work? Unfortunately not. That was the only possible solution. We checked it. It was extraneous. It was extraneous. Therefore, there's no real solution to this thing. No real solution to this thing. Now, before we move into this elephant problem, this was our first extraneous solution example. What made this one extraneous? And what made the other ones not extraneous? Or can we start picking out any patterns? You might start thinking about fourth power or fourth root or whatever. Okay, a little bit. But how about if this was a square root? A square root, would it still be the same thing? Sort of, yeah. The issue was raising a negative number to a fourth power and turning it positive. Remember how I said 2 to the fourth is also 16? If x was 2, if this was 2 on this side, positive 2, positive 2, positive 2, it would have worked. But the fact that it was negative means it didn't, and raising and turning it positive did. So it's this kind of issue that'll happen. Now keep in mind, we had a cube root problem with a negative. This one right here, cubing it kept it negative, and that solution still worked out. So if we're looking at some patterns here, the first one to look at is, now this is the only time that this happened, and it happened to be with an even power and a negative. Extraneous solutions can and likely will appear. Can and likely will appear. When I say likely, I think it's 100% of the time. When you have a negative on one side of the equation and you raise it to an even power to turn it positive. Assuming this one was positive to begin with. And it should be positive because you should have isolated this radical. If there was a negative on this side, it's a different story. But then you should have turned it positive, which would have turned this positive. So if this was negative and it turns positive suddenly, that's going to happen. So extraneous solutions will be existing. So I should be able to anticipate those ones when they happen. When they're positive to begin with, like all these, now this wasn't positive to begin with, but it turned positive when we added 10. If these, when isolated, are positive, I think you can expect that it should still work out. I don't want to be 1,000% because I haven't done these in a while to say, oh, is that always the case? And there are furthermore later cases where we're going to have to check for extraneous anyway. But that's just one of the instances where I think I can feel really comfortable in saying when I expect an extraneous solution versus when I don't. Okay, let's jump to number 13. Modeling with mathematics. Biologists have discovered that the shoulder height in centimeters of a male Asian elephant can be modeled by this function here. H equals 62.5 times the cube root of t plus 75.8, where t is the age in years of the elephant. Determine the age of an elephant with a shoulder height of 250 centimeters. So now we're going to substitute 250 for h and solve for t. No real difference from this problem than compared to others, other than it's a strange bit of numbers, right? We have to get the radical by itself, the cube root of t. And I don't expect extraneous solutions here, by the way. Let's first subtract the 75.8 from both sides, and we're going to get 174.2, I believe. I say I believe when these are where I make the most mistakes out of things, but maybe I should double check. Divide both sides by 62.5 now, right? We'll get the cube root of t equals 174.2 over 62.5. Now, I don't expect that to be super clean, but let's take a look at what that might be. First, let's do that subtraction. 250 minus 75.8. All right, 174. Okay, over 62.5. Okay, it's an exact number. It's a decimal, but it's an exact number, so let's write that out first. It's going to be 2.7872. Okay, now we're going to cube both sides to solve for t. This will be how old the elephant is to have such a shoulder height. So we're going to get t equals, it's going to be somewhere between 8 and 27, because 2 cubed is 8 and 3 cubed is 27. If I were to guess, I'd say probably around 18 or 20. I don't know. So let's cube this number, raised to the third power. 21.65. Let's round this. We'll say the elephant's around 21.7 years old. I do not know the lifespan of an elephant, much less an Asian elephant. Okay. All right, number 14. In an amusement park ride, a rider suspended by cables swings back and forth from a tower. The maximum speed v in meters per second of the rider can be approximated by v equals square root of 2gh, where h is the height in meters at the top of the swing and g is the acceleration due to gravity, 9.8 meters per squared second. Now, that's always the case. It's always that 9.8 number. And you might remember seeing that 16 number quite often for us that we've been using. That's for feet and seconds. This is meters and seconds, or squared seconds. Determine the height at the top of the swing of a rider whose maximum speed is 15 meters per second. Okay, so 15 is going to be v. We know g, acceleration of gravity, meters per squared second, is about 9.8. You're going to use that in physics quite often. And we're going to solve for h, the height of the rider at this moment. They're at 15 right here. So we are going to square both sides, and pretty soon I first want to multiply these two together to get 19.6h. That's a good start. Now we can square both sides in order to solve for h. 15 squared is 225, and this is 19.6h, and h will equal 225 over 19.6. Now we're going to round this. This answer will be in meters. So I get 225 divided by 19.6. And I'm getting 11.479, about 11.5. About 11.5 meters high. Like so. Okay. Okay. Numbers 15 to 26, solve the equation, check your solutions. Now this is probably where the majority of your equation should be focused on checking your solutions. I can't think. I'm trying to think of situations where you shouldn't be checking your solutions. I'm not saying I know when there will be extraneous ones or not. I'm saying these are the ones that should always have potential for it. When there's an x on the outside of here, you are now going to be turning, by the way, this is isolated, you are going to be turning what was linear into a quadratic, which means what probably would have just been one solution is now going to be two, also likely, also not necessarily, but could be. So expect a lot of extraneous solutions to come up here, guys. Probably just one per problem, but you have to double check both of them. So we square both sides. This is expanding this. We really got to get into our expanding binomials really good now. I'm not going to explain those. Subtract 3x to both sides to solve this, and when set equal to 0, try and solve by factoring, see if it's possible. This one can factor into x minus 12 times x minus 3. And then your two solutions will be x equals 12 and x equals 3. Now, I'm going to double check these ones. I'm going to write them on the side. There are instances where I'm probably going to be doing it mentally. But let's start by writing this one out. First of all, the original equation we're looking at is x minus 6 is square root of 3x. Remember, you can use any portion of the equation prior to squaring. And this happens to be the only step prior to squaring the original equation. Let's try 3. 3 minus 6 equals square root of 3 times 3. Negative 3 equals square root of 9. And you can see a hiccup here. Negative 3 equals 3 does not work. So x equals 3, no good. I don't know why I checked the right one first. But the left one, so that one's extraneous. That's an extraneous solution. 3 is extraneous. 12 minus 6 equals square root of 3 times 12. That's 6 equals square root of 36, or 6 equals 6. That one checks out. So there's only one solution to this, and it's x equals 12, whereas x equals 3 was extraneous. It's a solution to this portion of the quadratic, but not this portion here prior to squaring. So like I said, I'm probably going to do more mental work on some of these or less steps written, just so I'm not bogged down by way too much work that I'm doing outside of this. Your best to do as much as you feel you need to, but expect extraneous solutions to be had on many of these problems, if not all of them. Who knows? They really probably want you to test them. Number 16. And it's not that both were extraneous, right? Maybe just one of them. X minus 10 equals square root of 9x. Be helpful if I wrote down the correct original problem. Let's square both sides again. And this becomes x squared minus 20x plus 100 equals 9x. Same process as before. We're going to subtract 9x from both sides. I'm having a lot of trouble with the writing here. Equals 0. And this factors into x minus 25 times x minus 4. So these two solutions here are 25 and 4. Now this was the step prior to squaring right here, so let's double check in this one. We'll start with 25. Let's check 25 minus 10 equals square root of 9 times 25. 25 minus 10 is 15. 9 times 25 is 225, and square root of 225 is 15. And 15 equals 15. And that one checks out. We're all good on 25. Let's check on 4. 4 minus 10 is negative 6. And you can see where the wheels start turning already. Square root of 36 and negative 6 equals 6 is no good. X equals 4 is no good. X equals 25 is our only source of good. So once again, we have another extraneous one. You can hopefully see what's happening here that's causing this. I mentioned this in the lecture portion as well. You see, negative 6 may not equal 6, but when if I squared them, it would say 36 equals 36, right? All's good there. But it's because of squaring it that turns something that was possibly negative into a now positive. That's what's causing the issue. And does that always mean it's the smaller number that's going to work? No, not necessarily. It just depends on the nature of the problem. It depends on the nature of the problem and what you're doing with it, where the x's are, right? So number 17, we have square root of 44 minus 2x equals x minus 10. The radical is isolated. You can see we're doing a lot more square roots instead of cube roots and stuff like that, although it looks like we're going to hit some cube roots. And we get 44 minus 2x equals, this is again x squared minus 20x plus 100. Let's set them equal to 0 by adding this and subtracting that. We'll get x squared minus 18x minus or plus 56 equals 0. That factors into negative 14 and negative 4. And here we'll get x equals 14 and x equals 4. Now, again, I never seem to want to box these just yet. This was isolated from the jump, so we're going to substitute into there. Let's substitute 14. We get square root of 44 minus 2 times 14 equals, oh, this is just really low on room. Let's just do this one first, and then I'll do the other one next. Equals 14 minus 10, and that is the square root of 44 minus 28, which is 16. Square root of 16 equals, and that's 4. You get 4 equals 4. Now at x equals 4 here, we try the same thing. Square root of 44 minus 2 times 4 equals 4 minus 10. Uh-oh. That's 44 minus 8, which is 36, equals negative 6, and 6 equals negative 6. No good. Once again, the smaller number seems to be the wrong one here. And again, I do hope that they do diversify some of the problems up, so neither work, so both of them work, so only the smaller number works. It's very possible to make those ones happen. Okay, number 18. We have the square root of 2x plus 30 equals x plus 3. Okay. We will square both sides here. And we get 2x plus 30 equals x squared plus 6x plus 9. Subtract 2x over, you get 4x. Subtract 30 over, you get negative 21. This factors to x plus 7 times x minus 3. And your two solutions this time are negative 7 and 3. Positive 3. So as a double check, let's do 2 times negative 7 plus 30 equals, and this is negative 7 plus 3. This is negative 14 plus 30, which is 16. Negative 7 plus 3 is negative 4. 4 equals negative 4. No good. No good. So negative 7 doesn't work. But does 3 work? Yeah, probably. Square root of 2 times 3 plus 30 equals 3 plus 3. That's square root of 36 equals 6. And 6 equals 6 is all good. So x equals 3. That's a positive 3, by the way. X equals 3 is the only solution there. All right, let's go to numbers 19 and 20, where they are not square roots, but cube roots and fourth roots. Number 19, we have the cube root of 8x cubed minus 1 equals 2x minus 1. Okay, let's go ahead and cube both sides. Now, cubing this one's going to take a little more work, which is probably one of the reasons they're not doing a bunch of these. So 2x minus 1 cubed starts with 2x cubed, and then there's minus 3 times 2x squared times 1, plus 3 times 2x to the first times 1 squared. This is actually more work than I'll write in a future problem that we cube like this. Minus 1 cubed. So 8x cubed minus 1 equals, I got an 8x cubed here. This is minus 2 squared is 4 times that is 12, minus 12x squared plus 6x minus 1. Subtract 8x cubes. Those are actually gone, which is good for us. I want to get my quadratic positive, so I'm going to add 12x squared over. Let's subtract 6x, and let's add 1 over, which also goes away. We have 12x squared minus 6x equals 0. There's a greatest common factor of 6x, and inside here you're left with 2x minus 1. When you solve this, x can either equal 0, or if 2x minus 1 equals 0, you add 1 and divide by 2, you get x equals 1/2. So these are our two possible solutions. Now we're going to substitute them into here. I'll definitely work these ones out. Well, 0, 8 times 0 cubed minus 1, this is cube root of, by the way, equals 2 times 0 minus 1. Now, 8, that's all negative 1. Cube root of negative 1 equals 2 times 0 minus 1 is negative 1. You might say, uh-oh, but remember, you can take the cube root of a negative and you get a negative. So negative 1 equals negative 1 is all good. Let's try 1/2. Just write it over here. Cube root of 8 times 1/2 cubed minus 1. See, this expansion filled up all the space. Equals 2 times 1/2 minus 1. 1/2 cubed is 1/8. 8 times 1/8 is 1. 1 minus 1 is 0. You get cube root of 0. 2 times 1/2 is 1 minus 1 is 0. Cube root of 0 is 0. 0 equals 0. It checks out. So both work. There are two solutions to this one. They actually do both work out. Okay. Now, the idea behind this one, if we saw a graph of both of these things, well, I don't know what the cube root of 8x cubed minus 1 actually looks like, so I actually couldn't tell you. But the fact of the matter is there can be two solutions on these ones, and this time it actually happened to be an odd root, so maybe that starts to get you to think, well, can we have extraneous solutions with odd roots? I don't know. Maybe if we don't run into any, then we start to make conjectures, but it's the even roots that we know that things are probably going to. And not always. I can absolutely create an equation of my own with a square root, fourth root, whatever, that can have two solutions and both work, or two solutions and neither work. Things like that. Anyway, radicals isolated. Let's raise this to the fourth power on both sides here and now. We don't have to expand this fourth power thing. This just becomes 3 minus 8x squared, and 2x to the fourth, the quantity 2x to the fourth is 16x to the fourth. Let's get everything on the same side as the quartic function. So add 8x squared, subtract 3. Let's treat this like the quartic that it is. It's quadratic form. So we're going to have x squareds going on here and here. I'm going to shoot for 4x. I think this is going to work. 4x squared and 4x squared. And we'll get a positive 3 on one of them and a negative 1 on the other. That's 12x squared minus 4x squared, which is 8x squared. So that works out. This also factors. You can choose to factor it or just solve using square roots. This would become 2x plus 1 times 2x minus 1. This 4x squared plus 3 currently can't factor further, but we'll solve that part using square roots. So if 2x plus 1 equals 0, x would equal negative 1/2. If 2x minus 1 equals 0, x would equal positive 1/2. And in this case here, 4x squared plus 3, if that equals 0, we'll subtract 3 from both sides, and we'll divide both sides by 4. And we'll take the square root of both sides, and we get x equals plus or minus I root 3 divided by 2. Remember, with the square root, we do square root top and bottom. There is a plus or minus involved, so it's 2 more solutions. It was a quartic after all. So we get 1, 2, 3, 4 solutions. Now, there's a lot of double checking to be had here with all 4 sets. I don't know, I mentioned no real solutions for the first set. I don't know if they want imaginary solutions to be a part of them, or if they just want the real solutions, because if you imagine in these cases that we mentioned no real solutions to begin with, maybe these ones are also extraneous. We're talking about where these cross with graphs. So nothing wrong with these as far as you want to practice solving, you want to get them, sure. Real solution-wise, let's ignore them. They don't intersect on the graph. Listen, if I plug them into the original, I'm probably going to get statements that work, I guess. And that's more work than we probably need to deal with right now. So let's leave them. Let's go to these ones. Let's try negative 1/2 and positive 1/2. So fourth root of 3 minus 8 times negative 1/2 squared equals 2 times negative 1/2. And automatically, I'm raising concerns because 2 times negative 1/2 is negative 1. How am I going to, listen, even if this side becomes a 1 or whatever, how am I going to get a negative out from taking a fourth root of a number? Don't say if it's negative, because that would be, in imaginary cases and whatever. So this probably ain't going to work, right? Let's start this. Negative 1/2 squared is positive 1/4. Negative 8 times 1/4 is negative 2. 3 minus 2 is 1. Fourth root of 1 gets you that. So 1 equals negative 1. That's no good. So negative 1/2 don't work. Let's try positive 1/2. Fourth root of 3 is 2 times 1/2. So on this side, we're going to get 1, and the same thing happens. Positive 1/2 squared is 1/4, and the same thing. So here you'll get 1 equals 1, and that one will actually check out. So this solution works, and it's the only solution among the 4 that will work. And I say the 4 because keep in mind, the original was kind of just a quadratic. I mean, inside a fourth root. But it became a quartic. Remember, it became a quartic, right? It originally wasn't, and I think that's one of the things that we're really paying attention to. So just x equals 1/2 is the only solution that I'm doing there. Okay, number 21. You know what they didn't do, and I don't see it here later. They didn't have any, listen, your radical, before I move on to 21, your radical was always isolated on every one of these questions here. They really should have done one where it wasn't isolated to begin with, meaning this minus x, imagine that it said that to begin with. You'd have to add x to both sides before you start doing your stuff. So I'm surprised they didn't do them there. Listen, they'll probably get into them later, but I'm just surprised they didn't do any right there to say, make sure it's isolated first. All right, square root of 4x plus 1 equals square root of x plus 10. Now, both radicals are isolated. As long as one of them is, you're on your way to do what you got to do. Let's square both sides. We get 4x plus 1 equals x plus 10. You just get rid of the radicals. Subtract x from both sides. Subtract 1 from both sides. Divide both sides by 3. You get x equals 3. These questions will generally be easier than the ones with an x on the outside because of, from this current nature. Because what's there? Let's try 3. We get square root of 12 plus 1, which is root 13. Square root of 3 plus 10, which is root 13. That one checks out. It's all good. Feeling good about it. Number 22. This is one where radicals are not isolated, so we do have to isolate them to begin with. Square root of 3x minus 3 minus square root of x plus 12 equals 0. Let's add the square root of x plus 12 to both sides and isolate this thing. That way when we square it, we can cancel out the square roots immediately. So like that. So let's square both sides, and now square roots are gone, and we have 3x minus 3 equals x plus 12. Conventional solving, subtract x, add 3. Ooh, divide by 2, you get x equals 15 over 2. All right, 7.5. Why not? X equals 7.5. Now double check that one. We get 3 times 7.5, which is 22.5, minus 3, that's 19.5. So root 19.5 equals 7, and I'm going to use this one, by the way. 7.5 plus 12 is 19.5, so root 19.5. Hey, sorry, I wrote that with my mouse for some reason. Hey, that all checks out. We're all good to go. I'm just going to write a check mark on these. I am mentally double checking on some that I feel I can. Number 23, cube roots. Now, cube roots should have solutions. See, the thing about square roots, and I do want to bring those up again. Square roots, fourth roots, things like that, they are half parabolas. Not only are they half parabolas, well, I think that's a big part of it, that they don't go down on the other side, but cube roots have all real number domains. So they're likely to intersect each other somewhere, as long as they're not the same thing, like parallel. We're going to add this one over before we cube both sides, and them being cubed isn't generally a worse thing because nothing's going to be expanded. So we cube both sides here, right? Now we have 2x minus 5 equals 8x plus 1. We add that over, subtract that over, negative 6x equals 6, and x equals negative 1. All right, 2 times negative 1 minus 5 is negative 7, so cube root of negative 7 here. 8 times negative 1 is negative 8, plus 1 is negative 7. So on this one, we get cube root of negative 7 equals cube root of negative 7. And you can take cube roots of negatives. All those are good. So that one checks out. Number 24, also a cube root. Now, this one, couple things going on. We have one radical isolated. The other one is nearly isolated. It's not unisolated in a bad way, but you still have to be careful of one thing. We will cube both sides right now. As long as one's isolated, you're good. But keep in mind, when you cube this, you are also cubing the 2. In a product, it is this cubed times this cubed. So now we're going to have x plus 5 equals 2 cubed is 8. And this is 2x plus 6. But this is its quantity, like that. 8 times the quantity, 2x plus 6, as we canceled out the cubic. Now let's distribute. That's 16x plus 48. I want to subtract x this time. Subtract 48 this time. And you get negative 43 over 15. I don't love the answer. And I kind of don't want to double check the answer. But I kind of trust the answer, right? There's nothing algebraically I did wrong with this thing. So I'm just going to go ahead and say this one works. Now here's the thing, right? I trust cube roots being good. I just mentioned why. All real number domains means they're going to intersect somewhere. And if we found a point of intersection, it's going to be it. You can double check your numbers, right? Sys check your solution. Guys, I'm going to feel fine with that one there personally. So you decide on whether you want to double check. I'm double checking for extraneous solutions, not whether I did bad math. Okay, and I hope that makes sense. That's why I'm doing double checks on these ones, by the way, right here, when it's set equal, because I trust my own math leading up to it. And if I don't, I normally recognize those and I'll call attention to it. All right, number 25, we have square root of 3x minus 8 plus 1 equals square root of x plus 5. This is where problems get a little bit trickier. Now, to start with, I want to remind you that we have to make sure one radical is isolated, and you want one of them to be isolated. You don't want both on both sides, the same side of the equation. And it's impossible to isolate both right now. This one's isolated. We're in good form. Let's square both sides right now. The tricky part is the left side of the equation, because you have to remember that that is going to become a perfect square trinomial. Whereas the right side becomes just x plus 5. The left side has the following. Remember, we do a squared plus 2ab plus b squared. So a squared is 3x minus 8. Plus 2 times a times b times 1 is just this. And then plus b squared is 1. This is the expansion of this. It's not just this squared plus this squared. That's not how it works. It never has. It never will. We have to make sure that we understand that. Anyway, I want to simplify this stuff before I move on. Negative 8 plus 1 is negative 7. So I have 3x minus 7 plus 2 times square root of 3x minus 8 equals x plus 5. That's still a lot. But we have accomplished something. We got rid of one of our radicals. Now we still have one more radical to go. Let's get this one isolated now. So it's going to take a few steps, but we'll get there. So let's subtract 3x from both sides. Add 7 to both sides. And then divide both sides by 2. Now, if I divide both sides by 2, each term can divide by 2, right? So this will become negative 1x plus 6. Radicals isolated. Let's square both sides. So let's square both sides now. And this just becomes 3x minus 8. Awesome. This becomes a perfect square trinomial. A squared plus 2ab. The x is negative, so we're going to get negative 12x. Plus b squared, like that. And let's solve this quadratic. Subtract 3x from both sides. Add 8 to both sides. We get x squared minus 15x plus 44 equals 0. Negative 11 and negative 4 will be your two guys here. And we get x equals 11 and x equals 4. Is there potential for extraneous solutions? Oh, absolutely. We did 2 different forms of squaring. There's potential. And I believe there will at least be one. Let's do this mentally this time. Now, listen, we got to do it at any point before any squaring. That includes the original. That means we have to plug them into the original. So let's try and plug in 11. I'm going to go mentally. 33 minus 8 is 25. Square root of 25 is 5. 5 plus 1 is 6. Okay, remember 6. 11 plus 5 is 16. Square root of 16 is 4. Well, 6 equals 4. That doesn't work. So that is extraneous. Let's try 4. 3 times 4 is 12. 12 minus 8 is 4. Square root of 4 is 2. 2 plus 1 is 3. 4 plus 5 is 9. Square root of 9 is 3. 3 equals 3. x equals 4 works. X equals 11 does not. So that is our one solution. 11 was extraneous. I might want to look at some of those graphs eventually with you guys, but the bottom line is it intersected somewhere. Eventually, when we did squaring, whether it was the first time and or the second time, I don't know. But whether it was the first time and or the second time, somewhere we introduced solutions. I think it's the second squaring that caused it, honestly, because it turned this into a quadratic. I think probably in this stage, it still would have just been the one solution. So honestly, plugging 11 into here probably still would have worked. Actually, no, it wouldn't have worked. Never mind. All right, number 26. Let's do it on the next page. It looks like the first squaring is actually what did it in. Number 26, square root of x plus 2 equals 2 minus square root of x. Once again, make sure one, radical is isolated, and it is. So we can square both sides right now. You just got to be very good at your perfect square trinomial biz. So this becomes x plus 2. A squared is 4 plus 2ab. That's minus 4 root x plus b squared is x. Let's isolate this thing here. Now it's a negative 4 root x. I'd like for it to be positive. So honestly, well, let's still do this. Let's subtract x from both sides. Those will go away. Let's subtract 4. Actually, let's add 4 root x over. And let's subtract 2. There we go. I like that more. Let's divide both sides by 4. And you get 1/2. Square root of x is 1/2. Let's square both sides. And you get x equals 1/4. And there's only one solution to that. Let's see if it works. Before any squaring, 1/4 plus 2. I mean, we can call, 2 1/4. Let's just call it 2.25. We have square root of 2.25 on one side. And over here, we have, Over here, we have 2 minus square root of 1/4. So 2 minus 1/2. Wait, did I say that right? I think so, right? So that's square root of 2.25 equals 1.5. And yeah, and that, yes. And 1.5 equals 1.5. So that actually checks out. It was the only possible solution, and it was the one that we got. So 1/4 or 0.25, whichever one you want to write there, is what I'm getting. So number 26. Number 27. Oh, next set of problems. In exercises 27 to 34, solve your equation, check solutions. These ones have rational exponents. If you followed along with the lecture, we're basically going to raise these exponents. Well, we got to get them isolated, but then we're going to raise them to their reciprocal values because that's what cancels them out. So I'm first going to divide by 2, and then we're going to raise both sides to the 3/2 power. What happens here is these exponents multiply. 2/3 times 3/2 is 1, so you're just left with a 1x in this case. Now, where you have to be careful on this, and they didn't really mention this in the lecture portion, is that because you're doing to the 3/2 power, keep in mind what you're actually doing. You're actually cubing, and then you're taking the square root. If you're taking the square root, you actually have a plus or minus case on your hands here, right? Because we were raising to the 2/3 means you're squaring a number, and that number could have been negative. I don't believe the lecture portion actually did an example with that. So that's something you got to be careful about. Now, one solution might be extraneous, but the plus or minus is going to be involved. Now, this is the square root of 4 and then cubed. Square root of 4 is 2. 2 cubed is 8. So x equals plus or minus 8 is our set. And I probably got to separate them because we got to check and see if both will work. Positive 8 to the 2/3 power. Cube root of 8 is 2. 2 squared is 4 times 2 is 8. That works. Cube root of negative 8 is negative 2. Negative 2 squared is still positive 4 times 2 is 8. Both actually work. So you get plus or minus 8. There are actually two solutions. Again, I don't believe the lecture did one with this. So here's the thing you just got to, I'm raising this in red to make sure you understand. When you're raising this with a denominator that's an even number, that's an even root. That leaves plus or minus involved. And both worked. Nothing was extraneous there. Number 28. 4x to the 3/2 power equals 32. Let's divide by 4. Let's raise both to the 2/3 power. To the 2/3 power means we take the cube root and we square it. This one, because it's an odd root, doesn't have a plus or minus involved. Okay, so those guys cancel and you're left with x. The cube root of 8 is 2 and 2 squared is 4. X equals 4 is the only possible answer. And 4 is going to work. This doesn't seem to have extraneous bits. This is the same thing as the original problems that we had. In fact, I'm not going to double check unless there's another x involved on the other side of the equation, or unless there's a negative that we're doing something with in squaring or something like that. X equals 4 should be just fine in a scenario like that. Okay. Number 29. Number 29 is a different kind of story, though, because what happens here, I saw the equation and immediately I was like, all right, well, be careful. X to the 1/4 plus 3 equals 0. You subtract the 3 over, suddenly it's negative. Okay, this is where extraneous solutions appear more often than not. We raise this to the 4 over 1 power to the 4th power, right? This was the 4th root of x. Raise it to the 4th power to cancel that out. And now we get x equals negative 3 to the 4th is positive 81. Well, if you double check this, whether it's in this part of the equation or the original, 4th root of 80, or 81 to the 1/4 is 4th root of 81, which is 3. 3 plus 3 is 6. 6 doesn't equal 0. This is an extraneous solution. Therefore, no real solution to be had. No real solution in that case, right? That's where the difference lies. Again, there aren't going to be, to my extreme knowledge of this, and I really got to think over that before I say this as a certainty, but as long as that thing is positive on this side, I'm not going to bother doing a double check for it. We should be good. 2x to the 3/4 minus 14 equals 40, number 30. Add 14 to both sides and divide both sides by 2. And we get 27. Okay, we're going to raise both sides to the 4/3 power. That means cube root of, and then raise to the 4th. Cube root of 27 is 3. 3 to the 4th is 81. X equals 81 is an answer. It should be the answer. There should be nothing in extraneous harm's way, if that makes sense. Number 31. X plus 6 to the 1/2 equals x. Okay, it's these situations where you might want to double check things because now you have something outside of your radical. You say, Mr. Robinson, what radical? 1/2 power means square root of. And if you'd like to write that, go ahead. Listen, there's nothing wrong by turning this into square root of x plus 6 equals x if you feel more comfortable with it. You got to isolate this. It is. And, square it, right? Whether you write it like this or like this. Even if you write 2 over 1, that's totally up to you. We're squaring it. We're squaring it. So you're left with x plus 6 on the left side. You have x squared on the right side. Okay, it's a quadratic. We got to solve. Subtract x, subtract 6 to the side, set equal to 0. A lot of factoring, right? We're not doing a lot of quadratic formula on these ones here. So you got x equals 3 and negative 2. I would definitely double check these ones. Okay. This one's probably easier to look into as far as what you're doing. So let's try 3. 3 plus 6 is 9. Square root of that is 3. And that equals 3. We're good. X equals negative 2. Negative 2 plus 6 is 4. Square root of 4 is 2. Equals negative 2. No, negative 2 is not going to work there. Only 3 is going to work on that one. So that's one where you're definitely going to have to question whether the quadratic can have 2. I really want to find a quadratic that does have 2 solutions, though. It's possible to have, and I really want to. I want them to give us one. If not, I might have to kind of come up with one for you. I'll probably put in the description section and say, hey, check this one for yourself and do it. No promises, because I do the description stuff much later from the recording. I need to add 2x to both sides before I consider any squaring. Otherwise, it's not going to eliminate the radical. By radical, I mean the exponent. So now we're going to square both sides from here, right? That's a square root. We're squaring. Now we have 5 minus x equals, and 2x quantity squared is 4x squared. Let's solve this quadratic. 4x squared plus x minus 5 equals 0. Let's see if that factors. I think so. It should be. Let's see. 5 with the 5 and negative 1. Negative 4 plus 5 is 1. Yep. So we got x equals, subtract 5 divided by 4, you get negative 5/4 or negative 1.25. And you have x equals 1 here. Now I'm going to test 1 first. We can try it in the original if you'd like to. Remember, that's a square root. 5 minus 1 is 4. Square root of 4 is 2. 2 minus 2 is 0. 1 checks out. It's good. Negative 5/4, I don't know, likely to go kerplunk. I might have to write this out. 5 plus 5/4 is 25. 5. Oh, this is going to be troublesome here. So, wait. 5 plus 5 fourths is 20 fourths plus 5 fourths. We're subtracting negative 5 fourths. And we're taking square root of minus 2 times negative 5 fourths equals 0. This is 25 fourths, and square root of 25 fourths is 5 halves. 2, this becomes positive 5 halves. So you get 5 halves plus 5 halves equals 0. Oh, if only it was a negative 5 halves, it would have went, but it did not. So it doesn't work. Only x equals 1 works. Don't just automatically assume the fraction is the one that's not going to work. It just didn't happen to. All right, number 33. 2, oh, this one's going to be a little bit mean. Actually, it's fine. It's just a little bit mean. 2 times x plus 11 to the 1/2 equals x plus 3. Now, here's the thing, right? We always talk about isolating a radical. And by the way, this time I'm just going to rewrite it as a square root just to remind you that you can. Okay, so there's this, right? Same exact thing. We always talk about isolating radical. If, and I don't know if this helps or hurts. I think this will actually help to keep it like this. If we divide by 2, here's the thing. We got a fraction, right? And then we got a square with that, and maybe it's not as fun. You can square right now, and the radical will still go away because this is just a product. You can square here. When you can't square is if I had like a minus 7 or something like that, because that radical will not go away in that scenario. It'll only introduce it in a larger perfect square trinomial. We can square right now, and I'd prefer to do it right now to keep things intact as non-fraction. As long as you square the 2, people remember to square the 2 more on this side, even in fraction form. You do less so here. And I say that well knowing student behavior. So I got to warn you with that. Here's the other thing to warn you about. This is 4 times the quantity x plus 11. You square the 2, you get 4. You squared square root of x plus 11, you get x plus 11. It's the quantity. Okay, so just keep that in mind when you're doing it. So I'm going to square from that stage. It wasn't isolated, but it didn't hurt me. This is x squared plus 6x plus 9. I'm going to still distribute here. I get 4x plus 44. And let's continue solving this quadratic. You get x squared, subtract 4x, subtract 44. And this is factorable to x plus 7 times x minus 5. So x equals negative 7 and positive 5. Let's double check in this one when I wrote it as a square root. Remember, ditch the squaring, the squared symbols here. Negative 7 plus 11. Well, okay, let's take a look at this side. Negative 7 plus 3 is negative 4. You can't turn this one negative. So negative 7 is not going to work. 5 plus 3 is 8. There's no guarantee that that's going to work, but I'm just going to say that it will here. 5 plus 11 is 16. Square root of 16 is 4. 2 times 4 is 8. So 5 does work. Let's write x equals here. So x equals 5, not negative 7. There's your extraneity. Number 34. A quadratic inside a fourth root. We have 5x squared minus 4 raised to the 1/4 equals x. This is isolated. We'll raise both to the 4th power, right? 4th power, 4th power. Okay, this becomes 5x squared minus 4 equals x to the 4th. All right, treat it as quartic form. I will subtract the 5x squared over. I will add the 4 over. This factors into a couple x squared things. Got a minus 4 and a minus 1, which is fun because we got 4 solutions. X minus 1, x plus 1, x minus 2, x plus 2. And this factors into x equals positive 1, negative 1, positive 2, and negative 2. Which ones don't work? I don't know, maybe the negatives. And actually, when you look at it, yeah, it's the negatives that probably won't work here because this was just an x on this side, right? How are we going to raise something to the, or how are we going to take the 4th root of something and turn it negative with negative 1 and negative 2? You won't. So automatically, I'm already telling you guys, these two will not work. Will both 1 and 2 work? I should test that. 1, 5 times 1 squared is 5, minus 4 is 1. 4th root of 1 is 1. 1 works. 2 squared is 4, times 5 is 20, minus 4 is 16. 4th root of 16 is 2, equals 2. That works. So this is 2 solutions. X equals 1 and x equals 2. And that kind of makes sense. There was a quadratic inside your thing. It's not like we turned this into a quadratic. We did turn it into a quartic, however, right? So we introduced two other solutions that kind of weren't there to begin with. Okay, now, before we move on, I just wanted to restate the thing on number 27 and go back to it one more time. It was interesting that they introduced it and that wasn't in an example. This had two solutions. When you raise to the 3/2 power, better yet, when I rewrite this thing, this is the square root of 2x cubed. I'm going to do this one more time here. You can take the cube root of both sides to begin with. I'm sorry, I said that completely the wrong way. That is the cube root of 2x squared. Cube root of 2x squared. So if you take the square root of both sides to begin with, that's where that plus or minus is coming into form, right? Plus or minus. So this raising to 3/2 power, as long as your denominator is an even root, plus or minus will be introduced there. That was a trickier question with that in mind, but it did happen. So I expected more of those. Maybe we'll get more of those. We'll see what happens. All right, error analysis, numbers 35 and 36. Let's see what mistakes can be had here. Number 35, describe and correct the error. So they cube both sides. They didn't cube this side. That's not a common mistake. That was their mistake, but that's not a common mistake. So that's really interesting that they did that. They only cubed one side and not the other. There are so many different things they could have said as mistakes. Balance. Whatever you do to one side of an equation, you must do to another, right? That was kind of a weird error thing to speak of, just because that's not a common, maybe it is. I don't know. Anyway, let's solve it. Cube root of 3x minus 8 equals 4. As you can see what I wrote on the left side, you got to cube both sides. So this will be 3x minus 8 equals 64. 3x equals 72 and x equals 24 in this case, not 4. I'm not going to double check it. It's fine. It works out. All right, number 36. Number 36, we have 8x 8x to the 3/2 equals 1,000. Okay, this one's more possible to be had. You might not write the second step as it is, but this is a reminder as to why you might want to isolate this thing first, the x to the 3/2. Let me give myself some room here. Notice what they did on their second step. They raised both sides to the 2/3, which is what they're supposed to do, but the 8 somehow never got raised to the 2/3 power. It should be. Now, there are two ways you can do it. You can do what they did, which is keep it unisolated, right? You can raise the 2/3 power, but the 8 gets the 2/3 power as well. Or you can divide both sides by 8 to begin with. And 1,000 does divide by 8, so you can do it either way. So 8 never got raised to the 2/3 power. Now, that is the mistake. Whether or not you operate in that fashion, that was the mistake. So here's the original problem. There are two ways you can do this. One is follow their guides of always isolating your rational exponent term. So that means divide by 8. Divide by 8, you get x to the 3/2 equals, and 1,000 divided by 8 is 125. Now you raise to the 2/3 power so you don't make the mistake of doing before. Now, like I said, you generally want to isolate that thing. Generally, you have to isolate your thing. In this case, it wasn't a requirement. Maybe you didn't know 1,000 divided by 8. Anyway, this is x on this side. Cube root of 125 is 5, and 5 squared is 25, and that's the answer. Here's another version of it where you do have 8x to the 3/2 equals 1,000, and because it's a product, we can safely raise to the 2/3 power as long as both things get raised to the 2/3 power. 8 to the 2/3 power, cube root of 8 is 2, and 2 squared is 4. So you get 4, and this is x equals, cube root of 1,000 is 10, 10 squared is 100. Divided by 4, you get x equals 25. So it still works out either way, just their 8 never got cube rooted. And that was the thing I was stating before. If you don't isolate it, you might forget to do it. You might not write it this way, but you might forget to do it. You might write this still, and you still turn it into an 8, and then, something happened there. That's what happens more. That's what happens more. Trust me, I'm saying this from well over a decade of assessing students and student behavior of this kind of stuff. Trust me when I say that. All right, numbers 37 to 44, we solve the inequality. We got 2 times the cube root of x minus 5 is greater than or equal to 3. Now, first of all, let's establish your domain here, guys. We have an all real number domain for cube roots. X can be any number that you'd like it to be. Let's make sure we know how to solve inequalities. It's just like equations. The only thing is if we ever, and we'll see if it happens, but if we multiply or divide both sides by a negative number, the inequality's got to flip. I'm going to add 5 to both sides, treat it just like an equation. Let's divide both sides by 2 before we cube it. Yes, we can leave it there, but let's not get in that habit. Divide both sides by 2, and we get 4, and then we're going to cube both sides, right? So we cube both sides here, no change there. And x has to be greater than or equal to 64. If x ain't greater than or equal to 64, then this thing doesn't apply here. Domain's all real numbers, so we're good on any of those values there. No restrictions. Number 38 is also a cube root, so we should have an all real number domain here. No issues there. So we're going to, get cube root of x minus 4 is less than or equal to 5. Again, all real number domain. Let's cube both sides right now. That'll say x minus 4 is less than or equal to 125. That's 5 cubed. So x is less than or equal to 129. Now, this isn't a set that I'm really going to be looking to double check. But I want it, if you plug in, I don't know, 100 and, well, I don't know. If you plug in numbers that are more than 129, suddenly they won't be less than 5. I think that's kind of the issue. All right, number 39, we get square roots, and this is where we have to be more considerate with respect to our domain and what our final solution set will look like. And I'm curious to see what their later problems are going to be as far as how deep we get into this. So yeah, let's isolate this radical first. Let's talk about the domain first. X minus 2 has to be greater than or equal to 0. Whatever we take the square root of, guys, must be 0 or positive, so we have to be greater than or equal to 2. Whatever we get in our solution set here are bound by this restriction as well. Keep that in mind. Let's divide both sides by 4. And then let's square both sides, right? That's what's happening here. I square this side. I square this side. Add 2. We get x is greater than 27. Now, x must be greater than or equal to 2. 27 is already greater than 2. So I think we're good here that our domain is satisfied with all the solutions that have to apply here. So we're all good, right? We wrote that. We considered it. It just doesn't need to be spoken of. We say x has to be greater than 27. Oh, and by the way, x also has to be greater than or equal to 2. It's like, well, yeah, that 27 is greater than 2 or 28 or whatever. It's like, have you seen I don't think it's a spoiler. If you've seen Avengers Infinity War where, I don't remember the name of the giant elf or whatever they call them. It's the Peter Dinklage character. I don't remember his name. I haven't seen the movie in years. But where Chris Hemsworth, where Thor is trying to forge, get a star started to forge a hammer. I'm saying my stuff wrong. Anyway, Peter Dinklage's character says something like this would kill you, and then he says, only if I die. Yes, that's what killing you means. It's that kind of thing. X has to be greater than 27, only if it's greater than or equal to 2. Yes, that's what greater than 27 means, right? Or the other way around, right? X has to be greater than or equal to 2, only if it's greater than 27. Yes, that's what greater than or equal to 2 means. Anyway, I should have done some research on what those character names are. Let me know in the comments if you're doing these questions. All right, subtract 1 from both sides and you get 8. Let's also consider our domain. X has to be greater than or equal to 0 this time. Just as long as it's positive numbers, we all good. Let's divide both sides by 7. That's kind of weird, right? 8 7ths. Don't try and write the decimal version of that. And we're going to square both sides here. So I'm going to write that so we know you square 8, you square 7. X has to be less than 64 over 49. Now, 64 over 49, listen, that's 1 point something, right? It's a positive number, though. X has to be definitely less than 2, less than 1 point something. It can't be a negative number, though. So now we have to put these restrictions together. X has to be between 0 and that number here. It can be 0. It can't be 64 over 49. And there's our full restriction set as a compound inequality. Okay, now we're restricted as a compound inequality between two things. And those are ones where the domain must be applied. All right, number 41. Two times the square root of x plus 3 is less than or equal to 8. Our domain is the same on this one. Positive numbers are 0 only. With the less thans, I think we're going to have to really be considerate of that because we have to restrict it from it. Subtract 3, divide by 2, square both sides. You get 25 fourths. So as a combination of these, 25 fourths is 6.25. It can be equal to 6.25. It can be less than, to an extent. It can't be negative. So between 0 and dat 6.25, or 25 fourths, I'll leave it as a fraction, there is your solution set for that guy. All right, let's go to number 42. Cube root of. No domain restrictions on cube roots. So we all good there. This question actually seems easier than the majority of the ones that we've had. This is greater than or equal to 3. If I cube both sides here, I'm greater than or equal to 27. That's 3 cubed, and x is greater than or equal to 20. I'm all good there. No domain problems on a cubic. 42, very fast. 43, also a cube root. Shouldn't have domain restrictions. To my knowledge, we should all be totally good. Negative 2 times the cube root of x plus 4 is less than 12. We will divide both sides by negative 2. Cube root of x plus 4 is less than, this is division by a negative. This is greater than, flip the inequality when you divide by a negative, so negative 6. Maybe that's the trick to this problem. Did the other problem have that? No. Cube both sides, you get x plus 4 is greater than, cubing negative 6 is negative 216. Remember, it stays negative. So x must be greater than negative 220. And there ain't no issues with that thing being negative as a whole. We're all good there. Okay. And then finally, number 44, it's a square root again. Got a decimal. Now, when I see that decimal, I might rewrite it as its fraction equivalent, so we don't have to whip out the calculator. Negative 0.25 times square root of x minus 6 is less than or equal to negative 3. All right, first of all, negative 0.25 is also negative 1/4. I'm going to rewrite it like that so it helps you understand what it is we got to do to get this root x by itself. Add 6 to both sides, we get 3. And I'm dividing both sides by negative 4 is multiplying by negative 4. So multiply by negative 4 here, but the other thing to be careful about of that, of course, is the inequality flips. So the square root of x is greater than or equal to negative 12. Now, you might say in this situation, you square both sides. You square both sides. And this will say x is greater than or equal to 144. Now, this is one where you got to be careful for a couple things. First of all, if this was an equal sign, we've seen this plenty of times, guys. If this was an equal sign, remember, you plug in negative 12 here, suddenly it doesn't really work because we squared a negative and it turned positive. Inequalities can also lead to extraneous solutions. I haven't had to care about it before because it was always positive on the other side. This time it was negative. Try and plug in 144 or a number greater than, let's see, 169 is a perfect square as well, right? So let's try it right here. Try x equals 169. Does that work? Try on the one before we squared it. Square root of 160, whoopsie. Square root of 169, is that greater than or equal to negative 12? Well, that's 13. 13 is greater than or equal to negative 12. That does work. Okay, that does work. But if this was a less than, would have it worked? No, it wouldn't have. It would say 13 is less than or equal to negative 12. So you do have to be careful on extraneous. Did this work? It did. But here's the other thing you have to be careful of. Notice what I ignored this time, and I shouldn't have. I mean, I'm going back to it. Domain. X has to be greater than or equal to 0. So here's the whole, yes, that's what killing you means when we were talking about the other thing here. X has to be greater than or equal to 0, greater than or equal to 144 and greater than or equal to 0. But here's the thing. Both of these have to be satisfied, but this one was more in the extraneous realm. Do numbers greater than or equal to 0 still work? Try and plug in 1. What's the square root of 1? Square root of 1 is 1. Is that greater than or equal to negative 12? Yes, that's 1, greater than or equal to negative 12. Anything that's greater than or equal to 0 will work here. Anything that fits within the domain. Once this thing was negative, your test for extraneous solutions or bonus solutions or whatever you have start to take hold. This is where you just have to start to be very careful about it. And it's hard for me to talk about the rules of this one and how this problem is significantly more particular with what we have. But once this was a negative is where your particularities really start to come into fold. And this fold is, this may be your solution, but remember, this would have really fit the bill fine even with negative 144 greater than or equal to, but negative numbers can't go inside the square root. And that's where this thing gets a little bit different here. The solution to this, guys, is x is greater than or equal to 0. As long as you're greater than or equal to 0, you're good. It's the domain that overrides this thing. It has to do with this being negative, where you've got to start to do a lot more checks on these. I don't know how to state more on this one. This is a hard problem. Not from the beginning, maybe, or maybe, I don't know. There were a few things, right? Turn this into a fraction to help you, flip the inequality, all that. But there are more things to consider on a problem like this just because this was negative and we squared it, and that's what we had to talk about. I don't know if I explained that one right. I didn't know that was going to happen when it did, so that kind of caught me off guard to explain. Okay, number 45, modeling with mathematics. The length L in inches of a standard nail can be modeled by that rational exponent, where d is the diameter in inches of the nail. What is the diameter of a standard nail that is 3 inches long? All right, L is in inches. We're good there. No unit conversion. And we got this. We're going to solve for d. We're going to divide by 54. Now, 3 divided by 54 reduces to 1/18. So d to the 3 halves equals 1/18. We're going to raise this to the 2/3 power, both sides, that is. And there's nothing... 18 is not a perfect square, it's not a perfect cube, things like that. We're not going to be able to do a lot with that. We're more so just going to let the calculator do our work. So I'm going to do, in the calculator, I'm going to do 1/18 to the 2/3 power. And I get this number 0.145. I'll say 0.15. D is about... I don't know what D is measured in. D is about 0.15 inches. Remember, this is the nail's, diameter. Right? It should be small, right? I expect a small answer for something like that. So, there you go. All right, number 46, drawing conclusions. Hang time is the time you're suspended in the air during a jump, whether you're this animal or a snowboard. Your hang time t in seconds is given by this function, where h is the height and feet of the jump. Suppose, that aminal is a kangaroo. Suppose a kangaroo and a snowboarder jump with a hang time shown. All right, so let's start writing this out. 46. All right, t equals 0.5 times square root of h. Oh, hang time. All right, part A, find the heights that the snowboarder and the kangaroo jump. Okay, so height of kangaroo. Kangaroo. Their time is 0.81. 0.81 equals 0.5 times the square root of that height. Let's divide by 0.5, which is multiplying by 2. So we're going to get 1.62 if we do that. We get square root of h. And then let's square h, or let's square both sides. 1.62 squared is obviously something. I know it's more than 2.56. I'm going to say it's around 2.6 something. 1.62 squared. 2.6244. 2.6244 seconds. Because it's exact, I'm just not going to round. I'm just going to write it like that. So there's kangaroo's height. Now we need a snowboarder. And their height, their time is 1.21. Once again, we're going to be doubling because we divide by 0.5, so this is 2.42. And we are going to be squaring this. Now, 2.4 squared is 5.76. So square this, it's going to be a little more than 5.8. Or around 5.8, I should say. 2.42 squared is 5.8564. So 5.8564 seconds. All right, so there's the height of the snowboarder and the kangaroo based off that hang time. Remember, it's gravity that's involved. It doesn't matter what kind of animal thing you are. Part B, double the hang times of the snowboarder and the kangaroo and calculate the corresponding heights of each jump. Okay. So part B, double the hang times t, and then calculate the heights. I know where this question is going. So let's do Kanga. This hang time is now going to be 1.62, right? Doubled. We already saw that. But now we got to double said doubleage. That's 3.24. And the height in this case, 3.24 squared, probably around 10. 10.4976. Oh, I put seconds for all these. Guys, these are not seconds. What am I doing? These are feet. I'm so sorry about that. Feet, feet, feet. All right, snowboarder. Sorry about that. All right, 2.42 has to be doubled. 2.42. You know, it would have been better if I just rewrote the equation to get h by itself. Then we have to do this each time. I mean, we still have to do the same steps, but it doesn't look so weird. 4.84 is doubled. And now we square this number. This should be pretty close to 25, right? Because, you know, 5. I'll say 23 point something. Squared is 23.4256 feet. All right, their question is going to be regarding just comparing these things. When the hang time doubles, does the height of the jump double? Explain. Hang time doubled, right? We went from 0.81 seconds to 1.62 seconds. Then we went from 2.6244 feet to 10.4976 feet. No, that's not doubled. And this one's not doubled either, from 5 something to 23 something. So did they double? No. They did not double. In fact, they did do something though. And we've talked about this kind of stuff. They did not double. Whoops. In fact, they quadrupled. There are a lot of ways we can explain how this thing works. If we explain in terms of radicals, because that's the kind of section we're in, this is because these are radical functions. And your height, or your time, is a function of the square root of your height, which means your height is the square of, or is a function of the square of your time. So yeah, if you double your height, you don't double the time that you're in the air. You got to quadruple the height to double the time that you're in the air. Gravity has you, slow up fast enough for warp and fall down a little faster, that you need to compensate a little bit more than that to make sense of it. We've done that for surface area, right? If you double the length of the surface area, or of the length of an object, the surface area gets quadrupled. Instead, it's squaring. There's a quadratic nature to it. All right, 47 to 52. Solve the nonlinear system. Justify your answer with a graph. So number 47. Oh, good. They actually have, well, good in that they're having us check it and see how this works. Bad in that we actually have to graph. I don't know if we get to use graphing calculator or not. So y equals this, y equals that. The general things for these guys is we get to set them equal to each other to solve. So I can say like x minus 3 equals square root of x minus 3. Set them equal. Because we're trying to find what value of x gets you the same y, because they're both y equals. So I'm going to square both sides. Solve what we've been solving previously, right? So x squared minus 6x plus 9 equals x minus 3. Subtract and add those two terms over. Solve your quadratic. You get x minus 4 times x minus 3 equals 0. So x equals 4, x equals 3. Now let's double check these. In fact, no, you know what? In fact, they said solve the system. They said solve the system. So the idea behind this is when you solve a system, you're supposed to substitute 4 into either equation and it should work out just fine, and 3 into either equation and it should work out just fine. So here, when I substitute 4 into this, 4 minus 3 is 1 for y. Here, 4 minus 3 is square root of 1, which is 1. So there's a solution here that is, and that one checks out. So it answers 4 comma 1. 4 for x, 1 for y. That checks out. You substitute 3 into here. Whether you do top or bottom, you get 3 minus 3, which is 0. Square root of 0 is 0. So you get 0 out for that one, and that one checks out as well. So that's 3 comma 0. No extraneous solutions here. in that way of stating it, right? No extraneous solutions because it works for both sides of the thing. Now they said confirm with a graph. I'm going to use graphing calculators for these ones just so we're to scale. I know we could practice some of our graphs as well. Let's see. Justify your answer with the graph. Yeah, I'm going to do that because when I look at something like number 48, guys, I'm not going to really want to graph number 48. So I'm going to use the graphing calculator for those ones as a double check. So we'll go to the graphing calculator. I'm going to fix my window range on these ones so it looks good. The idea is these should intersect twice. I think this is our first time that we got two solutions. It crossed twice, right? Nothing was extraneous. So why did this happen? Because it's possible for a line to intersect a square root function, even half a parabola, twice. It's possible for it to hit twice, and that's exactly what this is going to do here. X minus 3, square root of x minus 3. Even if one of them hits at its vertex. So let's see. Here's the line. Here's the radical guy right there. Now, I want to zoom in on this thing right here because I need to show you exactly what it is that's happening. I'm going to zoom in this area here. Here's the line. Here's the square root function. Look at that. It intersects right here and right here. Now, these 2 points, I'm going to kind of copy, paste this thing over to our stuff. This is 3, 0. This is 4, 1. So it intersects twice. It hit at this vertex and it hit at that point right there. So it's possible for that to happen, and it did. There's the confirmation. All right, number 48. Same thing, set them equal to each other and solve. Now, I don't know what to expect regarding extraneous solutions or not. I have no idea. That one is just the first time that we had that. So I'm going to set x plus 5 equal to the square root of 4x plus 17. You might ask 2 questions. Does it matter which one we put first or second? No. I'll talk about strategically why I'm doing it. You say, then why do you keep writing this one first, the bottom one first? Because when I square this thing, that's what I'm about to do, I'd like my quadratic to already be on the left side of the equation. Squaring this expands this one. This is x squared plus 10x plus 25. Squaring this is just 4x plus 17. I get to subtract these over. So I want this on the side already. It's just a strategic thing. Does it matter? No. Do I like that more? Yeah. All right, subtract 4x and 17. You get this. This factors to x plus 4 times x minus 2. Oh, x plus 2. And so x equals negative 4 and negative 2. Now, you should double check these ones as well, right? Into both of them, really. This negative 4 gets negative 16 plus 7, which is 1. Square root of 1 is 1. Negative 4 plus 5 is 1, so they both work for negative 4. So negative 4 plus 5 equals 1, confirmed. Negative 2 plus 5, let's just do this. Y equals negative 2 plus 5, which is 3. Let's see if it works for the top one. That's negative 8 plus 17, which is 9. Square root of 9 is 3, so that one checks out as well. So maybe all of these ones are actually going to be ordered pairs. So when you plug in negative 4, you get 1. When you plug in negative 2, you get 3. These both work. Let's confirm with our graphs. So I'm going to sketch a graph of this one. I have to reset my window range, though. Maybe I should stay at negative 10 and 10 and just not worry about these things being so squared off. Because otherwise I have to do this each time. I wish there was a way to just reset these to defaults like that. Okay, so we're going to have square root of 4x plus 17. And then here we have x plus 5. All right. Big guy and this guy. If you can tell here as well, it does have that curve where it's crossing through. Just so I don't reset my window range each time, I'm going to keep it like that. Let's just copy, paste that, look that on this other side, and see that at least those are the values where they hit. So, you know, once again, when it comes to a curve, y'all, I'm gonna make this one more extreme, but this one's kind of curving like that, and then this one's going through like this, and it's hitting in 2 places. It's hitting here and here. So what are those 2 places? Well, negative 4, 1 is this one, and negative 2, 3 is this one. So that's the confirmation that it's hitting both of those curves, parts of the curve. Number 49, x squared plus y squared equals 4. I know this has two solutions because I know what both of these graphs look like. Wait, yes. This should have two solutions. Let me tell you beforehand what these graphs should look like so that when we solve, we feel better on this thing. I mean, they're going to graph it, but this is a circle with a radius of 2. The other one is y equals x minus 2, which is a slope of 1 that crosses through 2. We should get the solutions 0, negative 2, and 2, 0. This is my expectation, just so you know. All right, this is what we're going to be looking for here. Now, that's my confirmation with the graph. Let's actually solve this thing. This time I'd like to use substitution method. I'd like to substitute x minus 2 in for y in the top equation, like that. So it's not really a radical one, only when you graph it is if you use a graphing calculator, but x squared plus x minus 2 quantity squared equals 4. I mean, this is a straight up quadratic. There are no extraneous solutions in something that was always a quadratic to begin with, right? So this is x squared plus x squared minus 4x plus 4 equals 4. Subtract 4s, those go away. Combine like terms here, you get 2x squared minus 4x equals 0. Factor 2x out, you get x minus 2 equals 0. You get answers of x equals 0 and x equals negative 2. Oh, positive 2. Duh, I already told you that 2 would be an answer. So x equals 0, x equals positive 2. Now, because neither is going to be extraneous, right? I didn't square something that wasn't originally squared in the original equations. Because these should both work out when we substitute them in. So I'm going to plug them into the bottom equation. Y equals 0 minus 2, which is negative 2, and y equals 2 minus 2, which is 0. So when you plug in 0 for x, you get negative 2 for y. And when you plug in 2 for x, you get 0 for y. Did I not say these would be the answers? Anyway, if you don't know how to graph these circles on your own, given the center and radius and stuff like that, you can create the graph on the graphing calculator by getting y by itself. This is where the radical part kind of comes in. Y squared equals 4 minus x squared. Take the square root of both sides, you get y equals plus or minus 4 minus square root of 4 minus x squared. So you would create two equations. Y equals positive square root of 4 minus x squared, y equals negative square root of 4 minus x squared, and there's a third equation, y equals x minus 2. Both of these together make the circle. I'm going to graph that one more time for myself. Let me graph this one. Allow me this time. Maybe I should graph them when it's like easy graphs, and then I'll let the graphing calculator do it when it's not so easy graphs. So this one, well, I don't know. But anyway, this is a circle with a radius of 2, like that, for the first one. And the second one is y equals x minus 2, which is a y-intercept of negative 2 and a slope of 1. So that's where this is crossing like that. So those are those 2 points of intersection. Right there and right there. Okay, number 50. Another circle, another set, and I believe this will cross twice as well. I don't know if I want it. Oh. I don't know if this will cross twice. Let me talk about what this thing is and say, maybe it doesn't cross at all. I might just cross once. I'm not sure. I'm not sure on this one. We might graph this on the graphing calculator, but let me tell you my vision of this problem. My vision of this problem is this is also centered at the origin. The x squared plus y squared is 25, but this has a radius of 5. That means that this is at 5 right there. 25 fourths, guys, that's 6.25, which is up here. So with a y-intercept of 6.25, this slope is negative 3/4. It's possible this doesn't hit. It might not hit at all. It might just hit once. We might have something like this, just one solution. Or maybe it crosses twice. Maybe it goes through and out the other side. I don't actually know on this one. Very curious to see. I'm expecting maybe one solution here, or none at all. I'm expecting one, though. Maybe they'll get tricky. All right, substitute these things in. Now, this is where I'm going to get a little... I'm going to do this. I'm going to multiply both equations by 4. I don't want fractions. I don't want to deal with fractions with this stuff, even if they're just divided by 4. Multiply both these by 4, you get 4x squared plus 4y squared equals 100. And here, this is 4y equals... Oh, let's see. Does that help? I'm thinking about this. I'm thinking about what I want to do here. Do I have to deal with the fractions? Okay, I'm going to first multiply this thing by 4. I was going to tell you my plan. I wanted to make this thing say 4y equals, because I don't want fractions here, so negative 3x plus 25, like that. And I wanted to substitute 4y into here. The problem is, that's not a true 4y, right? So I'd have to multiply this one by 16 times 16 just to not have fractions. 16x squared plus 16y squared equals 400. Now, why do I need to make this 16y squared? Because 16y squared is 4y quantity squared. This is where I'm substituting this in for 4y. So now my equation will say 16x squared plus, and here's the 4y being squared. This is just so I can avoid fractions. Maybe the answer is fractions, I don't know. But this is where I wanted to start the problem. I don't want fractions, you don't want fractions. All right, this is 9x squared minus 150x plus 625. A squared plus 2ab plus b squared. So, at the cost of bigger numbers, I don't have any fractions. So 16x squared plus 9x squared is 25x squared. I'm going to subtract 400 over, and you get 225. These can all divide by 25, which is nice. So let's just divide by 25. You get x squared minus 6x plus 9. Hey, look at that. Yeah, there's only going to be one x answer here. This factors to x minus 3, and there's only x equals 3, right? Now, again, we didn't square something that wasn't originally squared in these equations, so this isn't extraneous or anything like that. So when we substitute that in for y anywhere you'd like, let's try it with the top one. X squared plus y squared equals 25. Oh, wait, no, I'm sorry. X squared plus y. X squared plus y squared equals 25. 9 plus y squared equals 25. Y squared equals 16. Y equals plus or minus 4. Okay. Now I plugged it into the top equation, which was a quadratic, which with the square root does have plus or minus. The bottom equation, this is my forewarning of this, the bottom equation would have only given us one solution, right? It was linear, not two of them. Which answer would have it given you? It actually would have just given you positive 4. We already saw the graph. This is where extraneous solutions, I guess, could potentially still occur, just the plus or minus aspect. This is where extraneous solutions could occur because of, maybe this is why they want you to test these. Because of, if we wanted to graph this, keep in mind, there would have been two different equations. X squared plus y squared equals 25. You get y by itself here. This is y is plus or minus root 25 minus x squared. But this line does not intersect with negative root 25 minus x squared. It only intersects with positive 25 root 25 minus x squared. So I'm going to use the graphing calculator for this to show you that the actual final answer is only 3, 4. This is a level of extraneity that maybe you yourself, maybe the book says, hey, solve this, get 3, 4 and 3, negative 4, go to the graphing calculator and find out, oh, darn, it's only one of them. So the graphing calculator is a confirmation of it. This is me by knowing the equation beforehand, what it's supposed to look like. But here are the two equations of the circle I'm going to put. This one and this one. These will both make the circle. Let me just show you that first. All right, we get a circle with a radius of 5 going all the way around here, okay? Next thing we're going to do is get this line. Now the line will just be out of reach from here. The y-intercept is going to be up here, and it's going to be coming down here tangentially. It's only going to touch it once at 3, 4, not at 3, -4. I mean, listen, you know it's a line, so lines can't hit both the bottom and the top unless they're going through a certain way. So the other equation is negative 3/4 x plus 25/4. And we're getting this line right here. It's just going to intersect once. Boom, at one point. That's at 3, 4. There's not another equation which is like positive 3/4 x minus 25/4, because if we had this one as well, where it's like a plus or minus thing, yeah, cool. We would have had bottom one right here, and it would have hit at that one, 3, -4. But we didn't have that, right? So technically something was squared that wouldn't have been before. I take it back. Technically, we did square this right here, I know we had this version of it, sorry. This was squared right here, which did kind of introduce something that wasn't there before. So the previous problem didn't have this issue. This one did. Okay, number 51. Well, more circle stuff. And 52 is more circle stuff. So this is just me needing to be aware of things. But it's a circle with a parabola. So x squared plus y squared equals 1. And y equals 1/2 x squared minus 1. Okay, this time I'm going to try and solve a different way. Is that okay? I'm going to multiply both sides of this one by 2, but not solving using substitution this time. Let's try elimination. Let's subtract x squared to this side of the equation. Remember the top equation was x squared plus y squared equals 1, right? We have x squared plus y squared equals 1. Let's subtract x squared to this side of the equation. We'll have negative x squared plus 2y equals negative 2. I'm going to use elimination this time and add down these lists. So this one goes away, and I'm going to solve for y first this time. We're going to get y squared plus 2y equals negative 1. Now when I add y 1 over, I get y squared plus 2y plus 1 equals 0. And this factors into y plus 1 quantity squared, and there's only one solution, y equals negative 1. Now when we solve for x, let's do the top equation, x squared. Well, let's not do the top equation this time. That's the one that leads to extraneity. Let's do the bottom equation. Negative 1 equals 1/2 x squared minus 1. I'll add 1 both sides to get 0. Multiply both sides by 2. And take the square root of both sides. You get x equals 0. So the only solution I'm seeming to get here is 0, negative 1. Which is interesting because this was a quadratic here. So I was saying, hey, maybe there will be 2 solutions this time. This is actually, here's what we're going to have. We're going to have a circle with a radius of 1. That means it's hitting a y-intercept of negative 1. But also, this parabola is also has a y-intercept of negative 1. But the stretch factor is so small that it looks like it's going to come around it, touch it just there. It's so compressed that it's going to do that, come around. This is the only point it seems like it's hitting. It's not sharp enough to come up and hit as many as 3 times. So it didn't seem to do that based off what we had here. That's my expectation. Let's go to the graphing calculator and see that. Now, when we do this, I need to rewrite this equation here as y equals plus or minus square root of 1 minus x squared. Subtract x squared over, take the square root of both sides. So let's go to the graphing calculator. Let's take a look at those ones. Plus or minus 1 minus x squared. So 1 minus x squared, negative 1 minus x squared. And then this other equation is 1/2 x squared minus 1. So your 2 graphs circle right there, a little small one. There's going to be a parabola going through and just touching, boom, the bottom right there. I'm not going to zoom in. You can go like it's touching everywhere up until that. No, it's just missing, and it touches that bottom right there. If it was a sharper graph, maybe it would have hit other points, but in this case it did not. The last question in this set is number 52. Okay, we have x squared plus y squared equals 4, and y squared equals x plus 2. Now in this situation, let's see. We have the circle on this one. I'm anticipating answers beforehand. I got a circle with a radius of 2. Like that. And we've done the sideways parabola things before. This is x squared is y squared minus 2. That's an x of negative 2. So I think it's supposed to be something like, maybe this one's not going to be so wide, and it's actually going to hit multiple times like this. I don't actually know for sure, but maybe we can have a 3 solutions case. So probably something like this is what I'm expecting at least. I expect negative 2, 0 to be an answer. The question is, what are these other ones? How do they work? Things like that. So we'll figure it out based on what's there. Now, this one's kind of nice because this is a direct substitution of things. X plus 2 can go straight in, not just for y, but for y squared, right? This is already y squared. So we can turn this into x squared plus x plus 2 equals 4, just like that, straight up. And I can subtract 4 over. And then this is factorable. So this becomes x plus 2 times x minus 1 equals 0. So x equals negative 2 and x equals 1. I don't think anything here should be in the extraneous realm because we didn't square anything that wasn't already squared this time. This was literally a direct substitution. But we have to now solve for y from these. Let's use the bottom equation, which just looks easier to work off of. So y squared equals -2 plus 2. Y squared equals 0, so y equals 0. -2, 0 was one of the answers I expected, so -2, 0. When y squared equals, or when x is 1, y squared equals 1 plus 2, so y squared equals 3, and there's the plus or minus root 3. And I expected two answers, one on top and bottom for that circle and the sideways parabola. Remember, because they're already set in squared form, this is a full parabola. It's not just square root of x plus 2. There's also negative square root of x plus 2. Which reminds me, we got to graph these. 1 comma root 3 and negative, and 1 comma negative root 3. We got to graph these, and when we do, we got to make our equations the right way. So what did I say? Plus or minus square root of 2. I got to write those. Square root of x plus 2. And then the other equations, y equals plus or minus root 4 minus x squared. So y equals plus or minus. So I got to do 4 equations here. So let me start typing those in right here while I just talk to you about that. So, again, these were already squared in this way. Circles are non-functions. Sideways parabolas are non-functions in that sort of way that, they're going to intersect in multiple formats potentially. And these ones seem to have that. If it was a half circle and a half parabola, they might intersect just once. They might not intersect at all, right? So those are the ones that you got to keep in mind when you're actually making them so. So square root of, let's see, negative. I'm almost done. Whoops, negative square root of 4 minus x squared. Okay, so I have in my calculator now these 4. Okay, here's the full parabola that's going to be graphed first, and then the circle, and then they should intersect at those kind of 3 points. So we got a circle, full parabola, top, bottom, and then circle on top and bottom that they intersect at, and I don't know if I've been copying and pasting them lately, but this intersects at -2 comma 0, and then it intersects again on top and bottom at, when x is 1, that must be positive and negative root 3. I mean, that's what we got for y, so, whoa, what did I just do? I hit a button that made everything go away, and I don't know what that button was, and that concerned me. I have to figure out what that was and not do that again. All right, so here's, you can't see anything that I'm putting. Everything just cleared out. I hit some button, and everything here just cleared out into just lined paper. I must have hit Control L. Oh, okay. Okay, now that one's locked in place. Yeah, so apparently, guys, Control J unlocks, Control K locks. I must have hit Control L, and everything wiped out like that. And I said, what happened? Anyway, Control K locks, just so you know why I sometimes do what I do. Anyway, -2 zeros here. This must be 1 comma root 3 and 1 comma negative root 3. Those are your 3 solutions there. All right, 3 solutions for that one. Let's carry on forward. We still have 11 questions to go. Number 53. Problem solving. The speed s in miles per hour of a car can be given by s equals square root of 30 FD. And the table shows the coefficient of friction for different surfaces. So s equals square root of 30. So that's F for this. They said compare the stopping distances of a car traveling 45 miles per hour on the surfaces given in the table. So we're going to do 45 for S, and we have the 4 different ones here. Number 1 is a friction on dry asphalt, dA. So 45 equals square root of 30 times 0.75 times d. That's 3/4 of 30, which is 22.5. So 45 equals square root of 22.5 d. I'm reckless when I do that because there's no guarantee that I'm actually right. Oh, what's 45 squared? Come on, Mr. Robinson. 2025 equals 22.5 d. And I need to divide that for certainty. Well, actually, I don't know that answer. Let's make sure that's 45 squared. 45 squared, and then divided by 22.5. Oh, it's an exact answer. All right, D equals 90. D equals 90. Stopping distance is in feet. I like the scientific stuff that they do. Shows that they did some work on that. All right, so for dry asphalt, that would be the one. Stopping distance 90 feet when you're 45 miles per hour. How about wet asphalt? A lesser coefficient of friction. more distance. So, wet asphalt. 45 equals root 30 times 0.3 times d. 30 times 0.3 is 9. So 45 equals square root of 9d. I think I can do this one. Square root of 9 is 3. So 45 equals 3 root d. Divide by 3. 15 equals square root of d. Square both sides. D equals 225. Takes 225 feet compared to the 90 feet on that one. Slick roads, man. Slick roads. All right. Also, snow should be the same thing. So snow, I don't know why they do that. D equals 225 feet. I'll just leave that as is. And let's just go up top just to fit this one here. Let's box these away. We have ice. Now, is ice going to just be, because it's 0.15, that's half of 0.3, is it just going to be twice as much? I would do some more work on that to be sure. I think the answer is going to be 1,000 feet. All right, let's see. So we have 45 equals square root of 30 times 0.15 times d. 30 times 0.15 is 4.5. So square root of 4.5d. Square both sides, you get your 2025 equals, that should be 20.25d. And divide by 20.25, that's d equals 1. That can't be 100. Hold on. Is it just 100 feet? No. No. Hold on. Did I mess something up? 20.25 times... What did I mess up here? Oh, dude, what am I doing? You don't square this number. 4.5 times d. Well, it's not 1,000 either. What did I say that I thought it was going to be? All right, d equals, in this case, 20. I guess there were some coefficients here that I didn't account for within this. This is 450. Oh, it is 450. All right, well, I guess I'm stupid. I guess these are proportional. Oh, you know why? Because it's inside the square root with d. This number's not changing. This the one that's changing. I got it. I'm good. I figured it out. Silly me. Okay, so next question. You are driving, part B. You are driving 35 miles per hour on an icy road when a deer jumps in front of your car. How far away must you begin to brake to avoid hitting the deer? Justify your answer. So your speed is 35 miles per hour. We're driving on icy road. Our coefficient of friction is going to be 0.15. So 30 times 0.15 times d. That's 35 equals, again, the 4.5d, and we're going to square both sides. 35 squared is 1225. This time I'm going to write 4.5 and not square the number stupidly. I was trying to fit the mold of the number 1,000 last time I did that. So this should be, I don't know, 1225 divided by 4.5 is, oops, I got a syntax error. Give me 1 second. This is 272.2 repeating feet. So how far away must you begin to brake to avoid hitting the deer? You don't round down to 272. You're going to hit the deer. You need to be higher than this. So at least 273 feet. You want to stop before hitting the deer. That's stopping power. Bum, bum, bum. So at least 273 feet away. Feeling a little bit better about life with that deer. All right. Number 54. Modeling with mathematics. The Beaufort wind scale was devised to measure wind speed. You bet. The Beaufort numbers B, which range from 0 to 12, can be modeled by B equals 1.69 times the square root of S plus 4.25. That's an S, that's a 5. Minus 3.55. S is the wind speed in miles per hour. We have some Beaufort numbers there for calm, gentle breeze, strong, gale, and hurricane. What is the wind speed for B equals 0 and B equals 3? Why didn't they say for calm, force of wind, and gentle breeze, force of wind? All right, so B equals 0 we'll get 0 equals this. Once again, someday I'll learn my lesson as far as rewriting this and solve for s first before I do anything else, but we might as well do it here. We're going to add 3.55 to both sides. We're going to divide both sides by 1.69. Now, that's not an exact answer. I'm almost positive of that. I'm not very positive at all. But I'm going to guess that's not an exact answer, so I'll probably leave it like that. Plus, there's another number we're going to have to do with that later. We're going to square both sides. So s plus 4.25 equals 3.55 over 1.69 squared. And we're going to subtract 4.25 from both sides. Okay. So, what is that speed? Oh, this is squared. I'm going to go to the calculator. And I'm going to type 3.55 divided by 1.69, put in parentheses, square it, and minus 4.25. And I'm getting 0.16, 0.16? Oh, it's calm. So 0.16 miles per hour. It says 1.1624, da-da-da, da-da-da-da-da. Beaufort wind scale, all right. So when B equals 3, now here's the thing, when B equals 3, guys, everything is going to be the same with the 1.69 minus 4.25 squared. The only different number is 3.55. Remember, we added it over, but we added it from 0 to get 3.55. This time it's going to be the same thing. I'm not going to do the same things twice. We add 3.55 over to get 6.55, divide by 1.69, square it, and subtract 4.25. So it's the same numbers, only instead of that being a 3, that'll be a 6. So when I change that to a 6, I'm getting the number 10.77. So I'll say 10.77 miles per hour. So there's a difference in wind speed between a calm wind and apparently that's still a gentle breeze. Part B, write an inequality that describes the range of wind speeds represented by the Beaufort model. So let's plug in 12. Well, hold on. I'm thinking about this where S has to, oh, that's negative 4.25. All right, well, by the Beaufort numbers, I guess the smallest wind speed we can have is 0.16 miles per hour that it can still register stuff. That's my guess, but we got to plug in 12 for part B. So part B equals 12 is the highest we got to take a look at. Now, when we do that, we're adding 3.55 to 12. So this time it's going to be S equals 15.55 over 1.69 squared minus 4.25. So let's turn that 6 that I had last time into a 12, or 15, sorry, because 12 plus 3. And I'm getting 80, ooh, hurricane, 80.41 miles per hour. So your range, if the lowest number, unless the lowest number is allowed to be 0, maybe it is, but your range based off the Beaufort numbers that we have go from 0.16 miles per hour to, and these are rounded, I guess, but 80.41 miles per hour. I don't know if this is saying this is what they can register. I don't know if they're saying that these are accurate, you know what I mean? Or if they're just saying that these are the only ones on the table that we're going to care about. That's the only part that I'm kind of a little bit iffier on, because maybe it's 0. When it comes to domain, it would be S is greater than or equal to negative 4.25, and I don't think we're talking about negative wind speed. So for Beaufort number stuff there, I think I'll go between those two, just based off those two numbers. That seems to be my max. I'm just going to go ahead and leave it like that, and those are in miles per hour. Okay. All right, let's go to number 55. Reasoning. Solve the equation. 55. Solve the equation x minus 4 equals square root of 2x. Then solve the equation x minus 4 equals negative square root of 2x. Okay. So this one, we square both sides. We get x squared minus 8x plus 16 equals 2x. Subtract the 2x over. Factor. and solve, and you get x equals 8, x equals 2. Now, when you double check this for extraneous solutions, 8 will end up working. You get 4 equals, square root of 16, which is 4. 2 does not work. This will be extraneous. So this is the first one. Now, the second one, check this out. We got x minus 4 quantity squared equals negative, the 2x there. Now, it's technically not isolated right now. Oh, why did I say squared? Oh, because I copied that over. This is x minus 4. X minus 4 equals negative square root of 2x. This is technically not isolated, but whether you apply the negative to this side or that side, it's not going to be any change once you square it. And I think that's what they're really talking about with this problem. Once you square it, you get to this stage right here, but then you end up getting out x equals 8 and x equals 2. And when you substitute these in, plugging in 8 this time gets you 4 equals negative 4, and that doesn't work. And you plug in 2, you get negative 2 equals negative 2, and it does work. So this one's x equals 2. So in one of them, this is extraneous, and the other one, that's extraneous. How does changing root 2x to negative 2x change the solutions of the equation? Well, in this case, and this is all part A, in this case here, it switches the part that's extraneous. There are 2 solutions originally, and the one that is extraneous, excuse me, the one that is extraneous for the 2 problems is swapped, right? We're swapping which one's extraneous. Part B, justify your answer using graphs. Well, I'm gonna do a rough sketch of the graph, and it's just because I've done so many, not because I've done so many graphs, because I've done so much explanation of this already, that this is a problem that, again, I explained before the book does. That's not the book's fault. They're doing it on their time. But I want to cover those things beforehand because not everyone's going to hit these problems. Anyway, so this x minus 4 is an equation. Looks like this. Y-intercept of negative 4 and slope of 1. Okay, so as far as this line goes, boom, 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 we'll get that going right there. All right, now the other ones, root 2x has a horizontal compression factor of 1/2. Origin is 0, 0. So I'll go 1/2 to go up 1, go over 2 to go up 2, go over 4.5 to go up 3, go over 8 to go up 4, and I think that one hits right there. So there's this one right here. When x equals 8, you have a solution for the top version of this, positive root 2x. Now, negative root 2x I'll do in purple. It's the same graph, but flipped over. This is 1/2 negative 1 at 2 negative 2, and look where this one hits. 4.5 negative 3, 8 negative 4, and then there's this one. So it's a full parabola when you consider them both together, but as 2 separate equations, you can see why they have 2 separate solution sets. Remember, we're only looking at the x values right now. This is negative root 2x, or y equals negative root 2x. This is x equals 2, and this is x equals 8. So that's what's happening there as far as confirmation. That's where we get those ones by graphs. Okay. Let me go down a little bit just so you can see the full graph. Okay, so that's what's happening there. That's why it's happening. Number 56. Your friend, very wrong friend very often, says it is impossible for a radical equation to have 2 extraneous solutions. Is your friend correct? Explain your reasoning. Of course your friend's incorrect. Your friend is incorrect. I have to make up one, though. Let's do this one. Square root of x plus 4 equals negative 1. Or positive 1, I believe. I want to make sure that that's right, that that's wrong, or whatever, that there aren't any solutions. You get square root of x equals negative 5. Wait. Two extraneous solutions. Let me think about that. Well, okay. I think you squared... Oh, never mind. That's just one of them. Your friend can still... Oh. me try this one. I'm thinking about the visual of graphs. So here's what I'm thinking about. Let's do a linear equation like this, and let's do a rational equation, you know, like this, and just make sure that one's never hitting the other. So let's do something like, now when you square it, I don't know if it changes things where they do hit. Let's try something like, I said your friend's incorrect. That might be premature. I've seen two extraneous solutions. I just got to think of how to make them. I think this should be it, right? X plus 5 equals, let's do square root of x, like that. So now when we square both sides, we get x squared. Now listen, this won't have x squared plus 10x plus 25 equals x. Subtract x over x squared plus 9x plus 25 equals 0. Now, this won't be factorable, but duh, if it was factorable, we'd have solutions. But these have... For the radical equation to have extraneous solutions, these are imaginary to begin with. Is that allowed? I got to think about that because these didn't have solutions to begin with. Because listen, these solutions are imaginary. So I'm just kind of playing with this thing. Can they be extraneous afterward? That's the thing I have to think about. When they say a radical equation, how about we do two radical equations? Let's do this. Let's do this. Let's do two radical equations. I still think I know your friend's incorrect because I've done it before. I just don't know how. Let's do two radical equations, but let's make sure that when they solve to begin with, when they solve in their quadratic form, they're still real solutions, but they aren't to begin with. So if I had, thing is, one of my radicals would have to have a quadratic inside. So I can't think of the graphs, but let's do something where you have some sort of like radical, but a pure radical, you know, like that. And then another one that's a quadratic kind of radical, but they'd have to cross twice. I'd have to come up with something here. X squared, I want to get good solutions here. Let's do, if I subtract x over and add 4. Okay, I'm going to get easy ones solving by factor. Okay, let's do a plus x so the x's will cancel. And let's make sure that this becomes positive here when you add the 3 over. I need a difference of 2 squares. Let's do minus 4. So let's do this one right here. When I square both sides, I'll get x minus 3 equals x squared plus x minus 4. I'm really just thinking about the quadratic. I want to solve the quadratic and see that these won't work as long as the number's small enough. Subtract x over, x's cancel, add 3 over, you get minus 1. This time we won't solve by factoring. Let's just solve using square roots. We get plus or minus 1. Now, when I substitute 1 into either of these, 1 minus 3 is negative 2. You can't take the square root of a negative. Doesn't matter that this is still negative 2. Square root of negative 2 equals square root of negative 2 are imaginary solutions. Doesn't matter that they match. They don't work. Negative 1's the same thing. Negative 4 equals, and apparently it's negative 4, square root of negative 4. Those don't work. These are extraneous because they get, what do you call them? They become imaginary in this original part. So your friend is incorrect. My friend is incorrect. Now, I forgive my friend on this one. But even the broken clock is correct twice a day. Man, coin flip, your friend should be able to get this one right or not. Just by pure luck. All right, number 57. Using structure, explain how you know the radical equation square root of x plus 4 equals negative 5 is no real solution without solving it. So this is the one I was talking about before. This is because the right side is negative and then it magically turns positive there, and that's why. When we square it, they said without solving it because you can't take the square root of a number, of a real number, and turn it negative. Right? That's why I was saying with the other ones before, listen, if it was positive, okay, you can solve, you're good. But you can't take the square root of a real number and turn it negative, and that's the issue. If it said 5, we're good. If it says negative 5, we're not good. Number 58, how do you see it? Use the graph to find the solution of the equation 2 times root x minus 4 equals negative square root of Explain your reasoning. The answer you're trying to solve for is for the x. They're intersecting at 5, 2. We're looking for the x value. The solution is x equals 5. It is the value of x of the point of intersection. That is my reasoning. It is the value of x of the point of intersection. And it's not extraneous or anything like that. We're not squaring anything. Those are the graphs themselves. That's where they intersect. The y value that you get out by plugging in x for 5 for x is 2, but we're not solving a system. We're solving this equation for x. You can try and plug it in. It should work. All right, number 59 on writing. A company determines the price P of a product can be modeled by that. They must have researched this chapter first. Where X is the number of units of the product demanded per day. Describe the effect that raising the price has on the number of units demanded. I'm trying to think if we're supposed to graph this or not. I guess we are, because otherwise it just gets really weird. So, if you raise the price, let's graph it. Now remember, raising the price is P, or Y, right? So let's get rid of those. Let's do P equals, or Y equals 70 minus square root of x. Now this is being subtracted, so I'm expecting something that's flipped over. I need to change my window range for this for sure. 0 for x and y, and then y goes up to at least 70. So let's put it up at 80 just to kind of see the tippy top is a for sure. And this thing probably branches out. That's a horizontal stretch. That's a massive stretch. I'm going to put this at 10,000 and see what's going on. All right, there's a nice effect of the curve. And it would keep going, right? I can go to like 1 million. You'll probably see a little bit more of it happening. There we go, right? We can make a lot of product. As the price increases, you have less, what's X? Number of units of the product demanded per day, right? Less demand. Higher price, less demand. I mean, that makes sense, right? Higher price, less demand. It makes sense in two ways. One, logically, like economically logically. Also, with respect to this function, this is a negative square root function. It's a negative square root function, and so it's going to be flipped over. The highest price we can set is $70, in which case we'd have 0 demand. From there, we lower the price some. We're going to get more demand. So I totally get it. I don't know if we were supposed to use the graphing calculator, but that confirms it. Number 60. City officials rope off a circular area to prepare for a concert in the park. They estimate that each person occupies 6 square feet. Describe how you can use a radical inequality to determine the possible radius of the region when P people are expected to attend the concert. Well, this is more of an area question, not equation. I was thinking equation of a circle, and I said, oh, never mind. That has nothing to do with this. Each person 6 square feet. P people are attended. If you multiply 6 square feet of a person times the number of people P, that cannot exceed, or that has to equal, let's see. Number of people are expected. Oh, inequality. That has to be less than or equal to the entire area of the park, pi r squared. So, it says describe. I'm kind of using this equation here. Again, 6 square feet per person times the number of people has to equal total is the maximum amount of area we can have. When it comes to radius, let's solve for r on this. We divide by pi, and we take the square root of both sides. We get square root of 6p over pi. Don't worry about negative radius. So that. So feet. It's not really a description other than what I said out loud, but this is the max area. This is the area of the region. We cannot exceed the area of the region. So I'll just say 6p is the area for all p people within the region, and it cannot exceed the area of the region. Therefore, whatever p is, you can plug that, however many people there are, you can plug that in. Oh, I'm sorry. I turned an inequality. I turned an inequality. So I got to flip the inequality because I put this on this side. Let me change that. So it should be greater than or equal to. Radius has to be greater than or equal to whatever area is occupied by that amount of people. Okay? Sorry about that. I was going to say, why is the radius changing size with people? No. Radius has to exceed that size. All right, number 61. 3 more questions. The Morokai, I'll say Morokai. The Morokai boulders along the coast of New Zealand are stone spheres with radii of approximately 3 feet. A formula for the radius of a sphere is this. Yeah, this is taking 4/3 pi r cubed, and I guess solving for, well, S is surface area. So they're doing a lot of work on this to get radius by itself. Okay, that's fine. Where S is the surface area of the sphere, find the surface area of a Morokai boulder. So we're going to substitute 3 and solve. Again, it's not a tricky question. It's just a substitution and solve for S. Multiply both sides by 2. Square both sides. And multiply both sides by pi. And this is in feet, so square feet for surface area. There's an exact. An approximated 36 times pi. We've seen that number before, I just don't remember it. 113 about. S is about 113 square feet. All right. 2 more questions. Number 62. Problem solving. You're trying to determine, 62 and 63 just look like so much fun. Look at these formulas. You are trying to determine the height of a truncated pyramid. Oh, we had tricky ones where we had to come up with a formula for its volume or something, which cannot be measured directly. The height h and slant height L of the truncated pyramid are related by the formula below. Whatever the height is, you can find slant height based off all this stuff. That's crazy. When I was saying we, it was IM2, I think chapter 11. IM2 chapter 11 that we had to do things with they didn't call it a truncated pyramid. They called it a frustum. A frustum where you do something with this. Anyway. In the given formula, B1 and B2 are the side lengths of the upper and lower bases. So when L is 5, so it's just a substitution. So L is 5. We got to find H, the height. We have B2 minus B1. We'll call it 4 minus 2. Let's square that. Wasn't there an H elsewhere? No, that was it? Okay, that's it. All right, so 5 equals square root of H squared plus 1/4 of 4 minus 2 squared is 4. So 1/4 of 4 is 1. Let's just square both sides now. I know I'll make sure to turn that into that. So we get 25. 25 equals square root, it's not a square root anymore. 25 equals H squared plus 1. Subtract 1. And take the square root of both sides. And you get, remember, there's no plus or minus involved here. I don't care to write 2 root 6. I'm going to be working this one out approximately. Square root of 24 is about 4.898. So I'll say around 4.9. Units. Are there feet or anything? I'll just say units. That is my height. Okay, so they're taking these things and make them a little confusing looking, but ultimately it's just like, all right, I guess there's not much to it. We're pretty good. All right, number 63 is our final set of questions because there are parts. Of course. Home stretch. A burning candle has a radius of r inches and was initially h naught inches tall. After t minutes, the height of the candle has been reduced to h inches. These quantities are related by this formula here. And there are a lot of variables. All right, h naught's the initial height. H is the height after some time t. And t is in minutes. Okay. K is a constant. Suppose the radius of a candle is 0.875 inches. Its initial height is 6.5 inches. And K is 0.04. Rewrite the formula solving for H in terms of T. What's K? 0.04. So we got to get H by itself. T will be in the answer. Okay? So that's part A. Rewrite the formula. Okay. First thing I want to do is square both sides right now. So 0.875 squared. Now 0.875 is 7/8. I might want to write that like a fraction, but 7/8 squared is 49/64, which I don't know what that decimal is. I guess it's exact. So let's see. 0.875 squared. 0.765625. 0.765625 equals. And we have 0.04t over pi times 6.5 minus h. Okay. I'm going to multiply both sides with pi times 6.5 minus h as a whole. So 0.76565 pi times 6.5 minus h equals 0.04t. Now, it's really about switching places. Actually, the pi can stay down, but now that I already brought it up, we can just bring it back down. I'm going to divide both sides by this here, and then I'm going to subtract the 6.5 after. So now 6.5 minus h equals 0.04t over 0.765625. I'd rather write the fractions of these, because I wonder if this is even like a perfect number kind of thing. 625 pi. Okay. If I subtract 6.5, then I got to divide by -1. So I'm going to do two things at once here. Subtracting 6.5 will make it negative, but dividing by -1 will make it positive. So I'll make the 6.5 positive. I'll make this part negative. And I wonder how much we got to do as far as reducing. The pi is going to stay as pi. 0.04t divided by this thing. Oh, it might not be clean, actually, because then you divide by 49. So 0.04 divided by 0.76565. Yeah, it's not a clean number as an overall. Let's just go ahead and approximate. Well, I don't know. Maybe there's a better... Maybe I'll just write the fraction version. The fraction equivalent of this is 64. Does that make sense? 64 over, let's see, h equals 6.5. I'm looking at my calculator. 64t over 1225 pi. That does make sense to me, at least, actually. So there's the exact fraction version. Your calculators can convert things to fractions. I wonder if I want to write 6.5 in like a, what do you call it? Common denominator? They said the initial height was 6.5, right? Yeah, so I don't know. I might just write it like that. So there we go. All right, so we're good there. All right, second part. Use your formula in part A to determine the height of the candle after it burns for 45 minutes. So we'll say 6.5 minus 64 times 45 over 1225 pi. All right, let's try that. So I'm going to go to my calculator. I'll do all that. 6.5 minus 64 times 45 divided by... When you do divide by 1225 pi, make sure 1225 pi is in parentheses. I'm getting 5.75 inches. So it started off as 6.5 inches. It only lost 3/4 of an inch over the course of 45 minutes, which is good. Which is good, right? We don't want to lose too many inches on that thing. So it looks like that would be it there. All right, guys, and that ought to do it for this one. This is Mr. Robinson. Thanks so much for watching. Next coming up is section 4.5 on, I actually can't remember what it is. Thank you. I think it's composition of functions or something like that. Or combinations of functions, something like that. All right. Thank you. Take care. I'll see you in the next one.